Sayın Rektörüm, Sayın Rektör Yardımcım, kıymetli protokol, saygıdeğer hocalarım, değerli katılımcılar. 15. Uluslararası Lif ve Polimer Araştırmaları Sempozyumuna hoş geldiniz. Tören programını arz ediyorum. Saygı duruşu ve İstiklal Marşımızın okunması, protokolün açılış konuşmaları, davetli konuşmacıların konuşmalarını yapması. Sizlerin başta Türkiye Cumhuriyeti'nin kurucusu Gazi Mustafa Kemal Atatürk ve ebediyete intikal etmiş aziz şehitlerimizin manevi huzurunda bir dakikalık saygı duruşuna ve ardından İstiklal Marşımızı okumaya davet ediyorum. Açılış konuşmalarını yapmak üzere Lif ve Polimer Araştırmaları Platformu Başkanı Profesör Doktor Yusuf Ulcal hocamızı kürsüye arz ederim.
Sayın Rektörüm, Profesör Doktor Mustafa Bertaş, değerli akademisyenler, araştırmacılar, öğrenciler, misafirlerimiz ve kıymetli basın mensupları hepinizi saygıyla selamlıyorum. Farklı üniversite, işletme ve ülkelerden katılan akademisyen ve araştırmacı dostlarımıza da katılımlarından dolayı hoş geldiniz diyor. Bu yılın toplamda 15.sini gerçekleştirdiğimiz Lif ve Polimer Sempozyumuna hepiniz hoş geldiniz. Akademisyen, evet arada böyle beni desteklemeniz için alkışlamanız güzel olur. Akademisyen ve araştırmacıların, sanayicilerin, projelere fon sağlayacak olan kurumlarımızın temsilcileriyle sektörün tüm paydaşlarını bir araya getirmeyi hedeflediğimiz bu etkinlik ülkemiz ve katılımcılar için önemlidir. Lif ve polimer ile alakalı başta tekstil olmak üzere diğer sektörlerimiz için de faydalı olacaktır. Uzun vadede ekonomik büyümenin sürekli kılınması teknoloji üretmeye bağlıdır. Teknolojik ilerlemenin de önemli bir kaynağı ülkelerin üretim yeteneklerini sürekli kılacak Ar-Ge çalışmalarına ayıracağı maddi kaynak ve önemli son derece ilişkilidir. Dünya genelinde Ar-Ge harcamaları 1995-2024 yılları arasında yaklaşık 500 milyon dolardan 2 trilyon doları aşarak neredeyse 4 kattan fazla harcamaya ulaşmıştır. Bu aynı zamanda küresel ekonomik gelişmenin üstündedir. Ar-Ge harcamalarını istikrarlı ve büyük artış eğilimi göstermektedir. Ülke bazlı sıralamalara baktığımızda ise Ar-Ge harcamalarında birinci sırada Amerika Birleşik Devletleri yer alırken Çin, Japonya, Almanya, Güney Kore, Fransa, İngiltere, Hindistan, Kanada, Rusya, Brezilya, Tayvan, İtalya, İspanya, Avustralya, İsveç, Hollanda, Türkiye ve ilk 20 içindedir. Çin ve Türkiye'nin son 10 yıl ortalaması itibariyle oransal olarak Ar-Ge harcamalarını en hızlı arttıran ilk iki ülkedir. Çin ve Amerika Birleşik Devletleri'nden her biri ayrı ayrı dünya Ar-Ge personelinin %20'sini barındırmaktadır. Amerika Birleşik Devletleri'nde Ar-Ge harcamalarının %55'i savunma sanayine, %25'i sağlık ve çevreye, %7'si ileri teknolojiye, %8'i uzay çalışmalarına ve %5'i ekonomik gelişmeye ayrılmaktadır. Avrupa Birliği'nde ise 27 ülke içerisinde %15'i savunma sanayine, %15'i sağlık ve çevreye, %45'i ileri teknolojilere, %4'ü uzay çalışmalarına ve %15'i ekonomik gelişime ayrılmaktadır. Japonya'da ise %4'ü savunma sanayine, %8'i sağlık ve çevreye, %50'si ileri teknolojilere, %8'i uzay çalışmalarına ve %30'u ekonomik gelişmeye harcanmaktadır. Dünyanın en büyük 20 ekonomisi içinde yer alan Türkiye ekonomisi hızla gelişen dünya ticaretinde önemli bir yere sahip olan 17. büyük ekonomidir. 2011 Ar-Ge harcamaları gayri safi milli hasılanın %1'i olarak gerçekleştiren ülkemiz bugüne kadar geçen yıllarda hedeflenen oranları %2 ve 3'ü maalesef yakalayamadı. İhracat içinde ileri teknoloji ürünlerinin oranı 2023'te %15 olan ülkemizin Ar-Ge harcamaları da %3'ler seviyesini aşmalıdır. Türkiye'nin ilk 10 büyük ekonomi içinde yer alması ve hedeflenen ihracat hedefleri ancak artan, efektif ve etkili Ar-Ge çalışmaları ile olacaktır. Türkiye ekonomisinin sağlıklı büyümeye devam etmesi ve bunun sürdürülebilir kılınması Ar-Ge çalışmalarının hem temel hem de uygulamalı olarak yer aldığı Ar-Ge faaliyetlerinin arttırılması ve sektörlere, ülke ekonomisine katkıları oranla yaygınlaştırmasıyla ancak gerçekleştirilebilecektir. Ar-Ge harcamalarını arttırmak ve daha verimli, etkin kullanabilmek hepimizin önceliğidir. Akademisyen ve araştırmacılar olarak kurumlarımızda yaptığımız temel araştırmanın sonuçlarını ticari ve uygulanabilir bir proje haline getirmek için sektör firmaları ve araştırma merkezleri ile üniversitelerimiz birlikte çalışmak zorundadır. Ar-Ge çalışmalarını inovatif konsepte dönüştürmemiz lazımdır. İnovasyonun ana unsuru ekonomik faaliyet ve ticari başarıdır. Türkiye'de reel ekonominin şartlarına da baktığımızda Ar-Ge bizim için uluslararası rekabet ortamında bir güç çarpanı haline getirilmelidir. Ar-Ge, paranın bilgiye dönüştürülmesi, inovasyon da Ar-Ge sonucu elde edilen bilginin tekrar daha yüksek paraya dönüştürülmesidir. Kısaca, inovasyon süreci sadece bilimsel bilgi birikimi, teknoloji gelişme ile ilgili değildir. Aynı zamanda ticari başarıyı da içinde barındırmalıdır. Değerli konuklar, bu sempozyumdaki amacımız akademik bilgi ve teknolojinin sektörün aktif oyuncularına transferini temin etmektir. Bu faaliyet ile hedeflenen firmalarımızın bilgiye dayalı ekonomik yapıya geçişlerine katkı koymasıdır. Bu organizasyonun oluşmasında emeği geçen tüm hocalarıma ve katkı koyan herkesi canı gönülden kutluyorum. Bu organizasyona destek sağlayan katılımcılara ve kurumlara da teşekkür ediyorum. Hepinize saygılar sunuyorum.
Sayın hocamıza konuşmalarından dolayı teşekkür ederiz. Hocamıza küçük bir hediye takdim edeceğim.
İçi boş ama kabul ediyorum.
Açılış konuşmalarını yapmak üzere Bursa Teknik Üniversitesi Rektörü Profesör Doktor Naci Çağlar hocamızı kürsüye arz ederim.
Sayın Rektörüm, Sayın Rektör Yardımcılarım, Sayın Lif ve Polimer Araştırmaları Başkanım, çok değerli akademisyenler, değerli konuklar, ben sizleri sevgiyle, saygımla, muhabbetle selamlıyorum. Tabii sempozyumlar akademik dünyanın kaçınılmaz etkinlikleri. Ama bu sempozyum ayrı bir özelliği var. Bu sempozyum yılda 2 defa organize ediliyor. Çok da sağ bir durum değil ama gerçekten zora talip olmuş arkadaşlar. Tebrik ediyorum. Yılda 2 defa organize edilen bu sempozyum ilkini Mayıs ayında üniversitemizde gerçekleştirmiştik. Orada da yine 300'ün üzerine katılımcı vardı. 60'ın üzerinde makale katılımı vardı. Bugün de yine burada da yüksek katılımla sempozyum devam ediyor. Bu sempozyum gerçekleşmesinin eline geçen sempozyum başkanı başta olmak üzere üniversitemiz ekibine, sempozyum ekibine teşekkür ediyorum. Ben de başarılı bir sempozyum diliyorum.
Sayın hocamıza konuşmalarından dolayı teşekkür ederiz. Konuşmalarını yapmak üzere İzmir Bakırçay Üniversitesi Rektörü Profesör Doktor Mustafa Berktaş hocamızı kürsüye arz edelim.
Saygıdeğer rektörlerim, değerli başkanım, kıymetli akademisyenler ve katılımcılar, öncelikle ve kıymetli sektör temsilcileri, 15. Uluslararası Lif ve Polimer Araştırmaları Sempozyumu'na hepiniz hoş geldiniz. Polimer, lif ve kompozit alanında uluslararası arenada güzide bir yere sahip ve bu alanda çalışan değerli bilim insanlarını bir araya getiren sempozyuma ev sahipliği yapmaktan ve sizleri ağırlamaktan duyduğum ekibim şahsım ve üniversitem adına duyduğum onur ve memnuniyeti ifade ederek başlamak istiyorum. Sağlık ve teknoloji temalı bir üniversite kuruluşu ile çıktığımız yolda önemli bir malzeme sınıfı olan polimere yönelik güncel gelişmeleri resmedileceği, farklı perspektifleri sunulacağı, sektörün önüne gelen şirketlerine yön gösterici nitelikte olan bu sempozyumun tematik anlamda bizim için önemli bir yere sahip olduğunu sizlerle paylaşmak isterim. Polimer bilimi, günümüz medeniyeti için sınır malzemelerin mevcut senaryosunda ilgi çekici bir alan olma özelliğini sürdürmektedir. Bunun nedeni, polimerlerin modern yaşamın birçok farklı alanında giderek daha önemli hale gelmesidir. Buna örnek olarak lif takviyeli polimer bazlı kompozit malzemelerin bazı benzersiz özellikleri araştırma, mühendislik ve endüstrinin ilgisini çekmiş, ilginin monolitik malzemelerden elyaf takviyeli polimer bazlı kompozitlere kaymasına yol açmıştır. Sürdürülebilirlik penceresinden değerlendirecek olursak, son yıllarda tüketicinin nihai bertaraf ve geri dönüşüm gibi süreçler de dahil olmak üzere yaşam döngüsünün tüm aşamalarında çevresel etkiyi dikkate alma konusunda duyarlılığı son yıllarda oldukça gelişmiştir. Buna ek olarak çevre mevzuatına ilişkin yaptırımlar, malzeme üreticileri üzerindeki baskıyı artırmaktadır. Dünya çapında artan çevresel farkındalık nedeniyle geri dönüştürülebilir ve çevresel olarak sürdürülebilir polimerik malzemelerin üretimine olan ilgi de buna bağlı olarak giderek artmaktadır. Cam veya karbon fiber takviyeli polimer kompozitler yerine doğal lifler ve biyolojik olarak parçalanabilir polimerlerden oluşan yeni nesil biyokompozit malzemelerin kullanılması, çevre sorunlarının ortadan kaldırılmasına da yardımcı olabilir. Daha iyi yaşam koşullarının ortaya koyulmasına imkan verebilir. Doku mühendisliği, akıllı ve medikal polimerler, giyilebilir teknolojiler, teknik polimerler, polimerik kompozitler ve polimerler için sürdürülebilirlik ve geri dönüşüm uygulamaları ile polimerlerin ileri üretim teknikleri gibi birçok tematik alanda bilgi ve çalışmaların sunulacağı, paylaşılacağı bu sempozyumun araştırmacılara, dinleyicilere ve sektör temsilcilerine eşsiz katkılar sunacağına inanıyorum. Sözlerime son vermeden önce bu güzide organizasyonun hayata geçirilmesine yoğun emek harcayan, organizasyondaki yer alan tüm ekibe, değerli katkıları nedeniyle bilim kuruluna, siz değerli dinleyicilere ve katılımcılara katkılarınız ve teşvikleriniz nedeniyle teşekkür ediyor. Hepinize saygı, sevgi ve muhabbetle selamlıyorum.
Sayın hocamıza konuşmaları için teşekkür ederiz. Sempozyumun ilk oturumunu gerçekleştirmek üzere oturum başkanı Profesör Doktor Cem Gök hocamızı kürsüye arz ederim.
Ses, evet. Sayın Rektörüm, Rektör Yardımcım, değerli akademisyenler, araştırmacılar ve kıymetli misafirler. Öncelikle hepinizi saygıyla selamlıyorum ve hoş geldiniz diyorum. İzniniz olursa yabancı misafirlerimiz de var. İngilizce devam etmek istiyorum. Esteemed Rector and respected Vice Rector, academics, research students, and our valuable guests. First of all, I would like to extend my warmest regards to all of you. Welcome to the 15th Fiber and Polymer Research Symposium. This symposium serves as a significant platform for distinguishing current research, technological and advancement, and collaboration opportunities in the field of fiber and polymer science. I hope that this symposium is similar to earlier ones. Our participants will leave the scientific gathering inspired by valuable insights and ideas shared here. Now, I would like to introduce one of the most valuable parts of our symposium, our keynote speakers. These distinguished speakers, known for their pioneering work in their respective fields, will share inspiring knowledge with us. First, it is my great honor to invite Professor Dr. Mehmet Özgür Seydibeyoğlu to this stage. Before we begin, I would like to present a brief biography of him. Dr. Seydibeyoğlu is a full professor at İzmir Katip Çelebi University. He is one of the founding faculty members of İzmir Katip Çelebi University with almost 13 years of faculty experience. Dr. Seydibeyoğlu has been researcher in various universities in Turkey and also Netherlands, Sweden, South Africa, United Kingdom, Canada, and USA. He has published more than 100 peer-reviewed journals with 2070 citations and H index of 25. He is one of the founders of the first biocomposite engineering graduate programs in Turkey, and besides, his studies at metallurgical and materials engineering department. He is also the head of the Department of Polymer Science and Technology graduate program. Currently, he is also leading a research group on biopolymer additives with 12 graduate students and 26 graduates. He will be sharing valuable insight with his talk. Now, you can start.
Hello, everybody. Good morning. First, I would like to thank the organizing committee for this fantastic conference. And I would like to express my sincere thanks to Professor Cemberk for his kind invitation for this conference. And so today, we will be talking about a natural nanomaterial, that's nanocellulose, that's obtained from natural resources. This is a picture of our university, from İzmir Katip Çelebi University, one of my pictures I took myself. And so this is the outline for my presentation. I will do a small presentation for our university, and then we will talk about sustainability and natural fibers and nanocellulose, and then nanocellulose-based composites that we developed, and the future outlook, and for any potential future collaboration that we can develop together, hopefully. So, as Professor Cemberk has mentioned, I have more than 25 years of experience. I published 3 books on fiber technology for fiber-reinforced composites, a book about lignin, and recently a nanocomposite book with different editors, one from Canada, one from Spain, and one from Thailand. So we also organized a Great Chemistry Conference at İzmir Katip Çelebi University in 2015. And also for this conference specifically, I would like to express that I worked in the industry for a while as well at Phloxar Group during my PhD as a part-time researcher. And after my PhD, I was full-time R&D executive at Acrylic Kimya, where I had the chance to learn a lot of acrylic fibers, carbon fibers, and acrylic nanocomposite fibers that I had developed myself, and a lot of things we did together. So this is our university. I've been there for almost 13 years now, and I've been there, and we do some courses outside in our garden, beside our canteen sometimes, and we do lectures in our class as well, with our graduates in our class. So we have a variety of equipments in our labs. We have furnaces, extruders, hot press, cold press, electroscopy, by Professor. So we got also ball milling devices, and we got all the thermal characterization tools as well. And what's our research direction? Actually, my research direction, when I look to the world, what we should do to the society for the world, I believe that there are so many things you can do in material science. You can go for functional materials, you can go for ballistic, you can go to energetic materials, but what I believe is that we need to protect our environment and our planet. So I try to work on sustainable materials and bio-based materials and circular materials, that we try to make new materials using wastes, bioresources, sometimes even titanium wastes from the implant industry. And we work on some nanomaterials as well, and advanced processing and functional properties. And most of the time I work with industrial partners that we try to make them available at the industrial scale. And this is the picture from University of Maine, where I was a visiting sabbatical professor over there. And this is the world's largest printer in the world. You can see they have 3 world records, and they make houses from biocomposites, they make boats, and so on. And I will mention about the biocomposite and nanocellulose research I've done there as well. So I would like to talk a little bit about sustainability issues. I also teach another course in our university on sustainable development. And why do we need a sustainable world? Some people try to find a new life on Mars or other planets. To go abroad, not abroad, to go another planet is exciting, trying to discover, explore the world. But, I'm sorry, we first need to protect our planet, right? We have a beautiful planet here, you see. This is one of the most famous pictures here, you see. This is another book I like a lot. This is the CEO of Arçelik, Hakan Bulgurlu. He climbed Everest mountain just to make awareness for the society about the climate change, climate issues. This is one of the beautiful Izmir photographs I have taken myself. So, guys, especially for our young students here, we need to protect our environment first. We have to sustain our world, right? And besides this, there's some nice young people as well, like Greta Thunberg, and she was 17, 18 years old once she was first activist, then she was a speaker at the United Nations and Davos Economic Forums. And she's saying our house is on fire, and I do not want her hope. I do not want her mercy. I do not want to be hopeful either. I want you to panic. I want you to panic as if we are on fire. As you see, last summer there was a lot of fires in our forest in Turkey. There are fires in Italy. There are fires in Greece. There are fires in US. There are fires in Australia. Those fires cannot be extinguished. So it's really on fire. Literally, we are on fire. And the temperature you see now is 25 degrees still. And in Fuji Mountain this year there's no snow. We are coming to November, becoming almost New Year. So it's obvious that we are in climate crisis. And by the way, I read a new book about carbon capture, and I noticed that, the first carbon emission was published, the first article, in 1896. 1896 arkadaşlar, let me say in Turkish as well. So it was 120 years ago. A Swedish scientist, Arrhenius, which is very important science for our metallurgy science, activation issues. He got paper on carbon emissions in 1896. So these are some pictures I took myself as well. These are from Maine. That's Maine area is the northeast of US. It's even higher, more upper north than Toronto, Canadian States. So it should be snow, right? But what happens? Last year, I followed some groups on Facebook. There was no snow in the Christmas time. Why a lot of celebrations and those things happen there, but there was no snow. That's happening in the world at the moment. And this is another group I follow about the sailing group. So there was a lake over there, but there's no lake left. Everything's evaporated. So we try to do some things in our university as well. I was the founding mentor for the Technology Association, and we try to make awareness for the students about recycling. So, and I was there with some students, as you can see me here. We were trying to make awareness in our university. And also I do some with high school kids as well. This is about, we're from Izmir Science High School, and we utilize waste from these plants, power plants, and this is flying ash, and we convert them to rubber hoses, and they got the first prize in Milliyetin Vakfı yarışması. And this is another thing we did a couple of years ago from coffee waste. We made some inks using the coffee waste. Now there's a company, Waste Espresso, thanks to them, they're doing fantastic work. And last May, with our new Materials Engineering Association, we did a recycling workshop. We invited people from metallurgy industry, from one-day recycling from Istanbul, from thermosetting composite industry, and one guy from LCA carbon footprint analysis. So, and also I did actually interview with a journalist about zero waste in 2016, and this journalist was actually the husband of our master student. He said, "Oh, this plastic is bad, sir." I said, "You cannot eat plastics for sure, but if you can collect them, if you can separate them nicely, then we can treat them nicely." But in our country, especially in Turkey, unfortunately, the first thing we need to. Can you hear me? Okay, it's much better. Oh, lovely. So the thing is, the first thing we need to put the trash into the can. So in 2016 we made this journal news, and then it was transferred to 2018 when this zero waste project came out. And especially for our foreign visitors here, at the United Nations and for our youngs, every March in the world now we are celebrating Zero Waste Day, which is fantastic, right? And so Sustainable Development Goals, you know most of them, but I would like to just give a couple of them about regarding cellulose, what cellulose can help. So we can have forest and marine products by the use of cellulose. We can help poverty. We can help zero hunger. We can make products out of cellulose. We can have good health and well-being. The cellulose resources are helping us to get oxygen. And we are talking about carbon capture. Cellulose is one of the fantastic materials for carbon capture. And so life on water and life on land. There's some other. And let me come to our topics. So, as Professor Cem said, I'm a metallurgical engineer from my undergrad degree. So formerly we were working on these materials, metallurgy. These materials are made at 1500, 1600. These are metal casting, steel casting process. So once you want to make a steel product, you have to go to 1600 or even sometimes for titanium, other alloys, 2000, 2500 degrees. But what happened is that the BMW car has transformed those chassis into carbon fiber composites in 2012, 13, and there's a lot of research going on to convert all the metal parts into composites these days. And besides composites, now what's the next generation is biocomposites. So this is a new car. So we transfer from steel and we reach to agriculture. I was doing my postdoc studies at the University of Guelph in Canada, in Ontario region, and I was a researcher at plant agriculture department. I was joking myself, hey, you start your career in metallurgy and you end up in crop science, agriculture. But that's the fact, and that's where the world is going, and that's where we should go to utilize these materials. And there's a variety of sources available, and cellulose, lignin, and hemicellulose is already a composite structure in itself. This is the picture. And this is one of the pictures I took in 2006 nanocellulose structure. And the natural fibers are already in the market used in certain applications, like decking materials, whichever you are using everything in your lives, and some automatic parts that are used already. And we did some studies on wind turbine blade design using natural fibers and bioepoxies. And you can see our studies during my postdoc studies in Canada we were doing. And nowadays, we opened a new course, it's an interdisciplinary course with mechanical engineering department. We are now designing wind turbine blades, and I'm also providing information in composite materials. And our professor, Sercan Acar, is a professor in aeronautics. He's more expert on design of these wind turbines, and we had a visitor from Enercon company in Izmir, a German company manufacturing turbine blades. So these are one of the last week image in our university. And what are the natural fibers? If you look at them, there's plenty of fibers, and nowadays there's too much incentive for our hemp fibers in Turkey. And there are a lot of projects coming up out of hemp fibers, which is fantastic. And my father is originally from Kastamonu region, north part of Turkey, where there's plenty of forest and there's plenty of hemp, flax fibers, and many other fibers. And in Turkish it was kendir, kenevir. Even my grandmother's surname was Ugani, which means kind of fiber, Ugani. So the advantage of natural fibers is actually they're lightweight, they're low cost, their biodegradability, and many other properties. And they're not strong as carbon fiber for sure. It's not easy to replace carbon fiber with natural fiber, but still there are some applications that also there are hybrid solutions that I will show in my presentation. So we are coming from the micro to nano structures. So it's nice to have this. And nowadays the nano structures are becoming commercially available as well. I brought a sample from a Turkish company here with me. A nanocellulose made in Turkey at the moment in Aydın, close to us, Izmir. So it's all natural product. It's 2% cellulose and 98% water. So we are now conducting some research with that company. If you like to me, I will give a little talk about your company profile as well. And this is the picture I took in 2006 when I was researching in Norway at NTNU. And these are the nanoclays during my PhD at Istanbul Technical University, where we could obtain some nanomaterials from natural clays. And that was TM images taken at Istanbul University. And so this is the electrospinning study we did with one of my PhD students. We converted lignin into carbon nanofibers by the use of electrospinning techniques. We have much more experts than me here in electrospinning, so I will try to skip that part. Okay, so what's the cellulose? What are the derivatives we are using for cellulose? Is cellulose-derived monomers. There are a lot of cellulose polymers, cellulose acetate and cellulose polymers. They are used at the moment already in the industry. And nanocellulose is one of the areas, and cellulose fibers now commonly are used already in a variety of textile industry and paint industry, carboxymethyl cellulose, in oil drilling industry as well. So today we will focus on the nanocellulose part. And why we are working nanocellulose is abundant in nature. That's the most important thing, guys. Because we are trying to survive our planet, and there is so much petrochemicals we are trying to extract from oil, from under the earth. We are trying to convert them to many reactions. We have some chemistry, chemical engineering professors with us, they know better than me. And so what's good is that the polymer is over there, already ready, just for us to use. And it's low cost, it's very stiff, more than 100 gigapascal, the modules value. And this is a very nice picture I love. Why? Because we have wheat straw, we have a variety of cellulose resources, guys. What we can do, we can get that fiber, separate the cellulose, and then what we are doing is we are converting that cellulose into nanocellulose. And what happened is that Pioneer company has used nanocellulose in electronic devices. So coming from wheat straw to electronic devices. And especially in Turkey, unfortunately, one of the speakers also told, we are not able to make high-end, high-technology products in our country still. That's kind of a lacking issue in Turkey. But they're also very important for biomaterials. And this is one of the themes of the conference this time, 15th ULPAS. And what are the already used nanocellulose applications? So this is a structure from Germany that they utilize nanosellulose in their structure. So it's now commercially used. And this is a 3D printed boat that the University of Maine has made, that they got 3 Guinness World Records. That's how I was inspired to go to Maine, actually. And once that they produced 1 ton of nanocellulose at the pilot scale at the university, that was one of my projects. In one of my projects, we procured nanocellulose from Maine. And the second thing was the 3D printing facilities. And this is a car made in Japan. There's a Dr. Yano, I really admire his work. This car has a lot of components using nanocellulose. So these things are now already used in some parts. Not very much large scale, but it's on the way. Besides these structural applications, if you go to electronic applications, you can see these kind of electrodes, substrates, or solar cell substrates, and so on. And also, you can see here, it can be used as cathode anode materials, and there's a variety of research going on to make light lithium-ion batteries, or fuel cell batteries. But what's happening now, we can make those anode and cathode materials from sustainable and renewable materials and from bio-waste. And there are some sensors made out of nanocellulose as well. And so nanocellulose we get obtained from trees, right? And we are getting from plant cell and getting these fibers inside. And what we are doing is we are separating the fibrils into nice nanofibers. That's the mechanical part people are doing at the moment. And this is the cellulose nanocrystals on the bottom left you see here. That's the cellulose are reacting with acid hydrolysis reaction, and the crystal parts are separated and amorphous parts are separated. Now we get really 5 to 10 nanometers thick and 100 nanometer long fibers, very, very crystals. Formerly they were called cellulose nanowhiskers, but these days they call it cellulose nanocrystals. And especially for this biomaterial world, that's for the theme of this conference, the bacterial cellulose is one of the fancy ones, and it's now commercially used in Korea, in some Asian countries for facial applications, for some cosmetic applications, and in Turkey there's a lot of groups in Bartın University, in Ege University, Celal Bayar, Manisa. Many people are now making these bacterial cellulose. So microfiber cellulose can be obtained from different resources, wood, sugar beet, potato, ham, flax. So you can imagine, you can get all these materials from everywhere. And NCC is about wood, cotton, ham, flax, wheat, and bacterial cellulose could be one of the bacterial cellulose are Acetobacter xylem. We made a publication together with the Imperial College London on bacterial cellulose, but there's unlimited source for bacteria to make the cellulose material. So the rest is temperature. One of the things is high temperature performance is striking one, and thermal stability, high elastic modulus, gas bearing properties. These are important for sometimes packaging materials, for polymers. Sometimes it's used for hydrogen storage tanks, and it's lightweight as well. So the paper and cardboard industry are now commercially using nanocellulose. There's a lot of companies, a Dutch company, SAPI, a Dutch professor is with us here from Netherlands. So, and SAPI has a plant in North America, in Maine as well. They have a plant in South Africa, the countries I have been. It's a nice company for me. And concrete is now becoming more reality, especially in North America. And with Fiber Kimya, we are trying to implement these fibers in paint and coatings, cosmetic industry, in some applications, and some other air filter, water treatment. We have some professors here from water treatments. They are working on these things. And so most of the things are on the experimental level, to be honest with you, but some things are, especially paper and cardboard, are now a reality. They are used at the commercial scale. So let me come to my studies after all these talks. So this was my first paper, actually, to be honest with you, it was 2008. And that was published with Christina Oxman. She is one of the leading people in this area on nanocellulose. She is now in Sweden. And what we did, I was a recipient of Norwegian scholarship to be there for 5 months. She was there in Norway at that time. And we converted these cellulose fibers into nanofibers. So, and by using a high pressure homogenizer. I bought this machine in our university as well, at İzmir Tiyatro. And the sales guy was surprised, what are you going to do with this shirt? I'm going to make some nanofibers. Oh, we are using for some fruit and some other food applications. And This is used for high-pressure homogenizers to make nanofibers. And we obtain some colloidal dispersions. And you see the left side is the micron-sized cellulose with polyurethane, and the right side is nanocellulose, the same polymer, the same cellulose, but one is micron scale and the other is nanoscale. So the pictures are now becoming transparent, as you see. It's really nice picture, I like. It was just a random photograph I took, but still it's amusing. It's not the transparency, but the strength-wise, from 5 megapascal, we went to 28 megapascal. And modules-wise, from 25 modules, 700 megapascal. So it was like 20-fold, 25-fold increase in strength and modules, and 5-fold increase in strength. So the DNA graphs also showed similar data. And during my postdoc studies in Canada, I was at the University of Guelph, and we were collaborating with Imperial College London about bacterial cellulose. And you see the fibers here, and now they're finally dispersed in a polyurethane solution. But once we look at the microscope, TM images and AFM images, we could see the fibers are well aligned and well dispersed. And mechanical strength from 3 to 6 megapascal, 100% improvement, and modules around 50% improvement. So the DNA graphs are also confirming our mechanical tests as well. And during my study at the University of Maine, we worked on nanocellulose hybrid structures. We published 2 review articles, and we didn't publish these data due to some confidentiality issues, but I can probably share some of them. We use some nanocellulose fibers with some wood fibers with PLA matrix, so it's 100% bio. And we did some 3D printing studies as well, compounding studies, drying, and a lot of stuff. So I can share a couple of them. That with the hybrid component with 5% wood and 15% CNF, we could obtain almost 100% improvement in strength. And sorry, modules value. Strength-wise, it was similar. The flexural modules also was almost 100% improved. And I would like to take your attention to one of our recent studies with my PhD student, Alper Doğru. He is also a lecturer at Ege University Aerospace Vocational School. And we applied for a patent as well, with PhD. And we published 2 papers this year with him. One is at Progress in Additive Manufacturing, and one is in Rapid Prototyping Journal. So we have the same figure here, and we got the nanocellulose from Maine. What we do now, we are using the nanocellulose not solely. We are getting hybrid structures, and we are coating the carbon fiber and glass fiber with cellulose nanofibrils, so that we can get a nice homogeneous structure. And we use carbon fiber, glass fiber from Turkish resources, and we use polyamide 6, and we did twin screw extrusion, thanks to Eurotech company from Çorlu. So we could get these kind of compound granules. And in the second stage, we utilized CNF. We coated these fibers with CNF solutions. This was taken from University of Maine, from my previous project, but nowadays we are working with a Turkish company that I will mention as well. And we did some strict acid modifications and coated the fibers with CNF. And then we applied similar research and coated them and obtained the granules. And after that, thanks to Sadık, here you see a professional company owner, AG Plastic, so that we could obtain nice filaments. So we don't only make compounds, we also make filaments out of it, and carbon fiber, glass fiber, and we also made a hybrid fiber. That was an interesting part of our PhD. Okay, there's carbon fiber available, but 10% carbon and 10% glass fiber hybrid structures, and we extruded them. And this is a partly, Alper was a visiting researcher at the University of Alberta during his PhD, but thanks to Jubitak, the Uniki 2214 project. And we could obtain similar, this time we obtained cellulose modified filaments. And we did some 3D printing studies, and we could get some tensile bars Sharpie bars and test geometries. And this is the Ultimaker printing now, you can see here. And you could open all these things. Production. So you can see many tensile bars. Thanks to Adrian for this fantastic and tedious work. So the thing is, I would like to just mention here that I know it's spending a lot of time. That we are starting from 30-40 megapascal, and we are reaching 130 megapascal from polyamide, and by utilization of different processing conditions. That's the most important outcome of this data. Because I can talk for hours and days for this data, but the thing is, first of all, the hybrid fibers are promising because the carbon fiber is expensive, but we can replace the carbon fiber with glass fiber at a certain ratio. And second thing is our operating processing parameters for the printing is affecting our final properties. That's the outcome of this data. And also, this is the cellulose modified data. So the first ones, as you see here, are pure polyamides, this one, and these are carbon fiber, the one, and then just next to it is cellulose modified. So 1% of nanocellulose could improve the strength of our materials. And we obtained similar improvements by the use of nanocellulose at a variety of concentrations, actually, glass fiber, and even hybrid fiber. So the last part is about the hybrid fibers. So nanocellulose. And also for layer height from without nanocellulose and with nanocellulose, the left side are with nanocellulose. And for, again, tensile strength, this is for carbon fiber 20, this is carbon fiber 10%. And if you look at the impact test, by the use of nanocellulose, we could obtain 18%, 12% improvements in impact studies as well by the use of nanocellulose fibers. So the reason is actually, you can see the hybrid fibers here. The one is actually the beam structure of carbon fiber, and the other one is glass fiber. If you look at here, now we have this nanocellulose coated SEM images that we see very nice composite formation by the use of nanocellulose. So, what are the future outlooks? The use of thermostatic composites and hybrid composites, advanced applications, coatings, drilling fluids. Lignin, we have published a new book chapter on lignin containing CNFs. Also, a Turkish company, Fiber Kimya from Nazilli area, they are now making nanocellulose production that here you can see in my hand. It's 2% weight, just cellulose and water, 98%. So there's a nice schema over here, and they're getting actually mechanical grinding and applying some Masuka grinder and other processes, and they're obtaining this nanocellulose at the moment in our home country, Turkey. So there's a variety of areas we can apply, but still it's in R&D process. And before concluding my remark, I would like to thank many people in my life. So this is Chris Nelson, my first paper co-author, which I was lucky. She's now about 40,000 to 50,000 citations. And Amar Malanki and Majid Isra, they're at the University of Guelph. They have 80,000, something over 70,000 citations. And they were at Michigan State before. And I was following them even at Michigan State. And these are from Netherlands, from Ferry, actually, Saxon University. Last year I was with him. And this is Richard Arm from Nottingham Trent University. We worked in Izmir in another conference together. And after that conference, I had the chance to work with Richard Arm in 2017 in UK, in Nottingham, on 3D printing. We were making really fancy stuff that I didn't show here. And this is Douglas Gardner from University of Maine. And a couple of weeks ago, he was in Izmir, in Kuşadası. Had a nice dinner with him, with his American friends. And besides are a couple of my grad students here. And this is new graduates last summer from our university. And these are some books I just got from an old elderly friend. And this is my wife, Elif, from Ege University, Chemical Engineering Department, and our daughter. She's now older. And this is our final photograph from our university. And I would like to thank all of you for listening this talk. And thanks again, Professor Cenk and Professor Demir, for inviting me for this talk. And any questions are appreciated.
Thank you, Professor. It is very valuable and important speech. Now we will move to question and answer session. Genç arkadaşlarımız da var. Belki Türkçe sormak isteyen olursa çekinmesin. Kendini tanıtarak sorusunu sorabilirler. El kaldırabilirsiniz sorularınız varsa.
Thanks, Professor Özgür. A very nice presentation. I have a quick question about the transparency of the field. Maybe you explain for the audience what is the reason that crystal nanocellulose is making a transparent film, but the other one is not.
So actually, the nanometers below 200 nanometers, by the law of physics, actually, as the crystals are now separated from each other, so that the light can pass through easily. It happens actually in glass materials as well. Why is glass transparent? I ask many undergrad students as well, because it's amorphous structure. So the light can penetrate through it, so the nanometers below 200 nanometer the light can pass easily. So thanks for this nice comment.
And yeah, very nice, and probably even in the bottle, like polyester bottles for Coca-Cola, etc., is transparent, and the crystal size is there is also very small. And when the crystal size is smaller than the wavelengths of the colors, especially 400 nanometers, then it's not visible. The crystals are there, but you cannot see with the normal eyes, and it's transparent. Thank you.
Once you remove the lignin from the wood,
Well, actually, I'm not a bioengineer or not a wood scientist, unfortunately. I don't know how to separate. We did a couple of studies, but I'm not an expert. But I also worked on lignin as well. We utilize lignin in polymer composites. We published PP lignin composites, and one of my PhD students actually published a paper on we convert lignin and PAN blend, 85% lignin containing blend, into nanofibers, and then we made carbonization process, and we made carbon nanofibers, and they are used for electrode materials for batteries or some biosensor applications. So there were a couple of studies we did on lignin, but nowadays I'm not much working on lignin.
More question? Sorunuz var mı arkadaşlar?
Türkçe'de sorabilirsiniz arkadaşlar. Yani Türkçe'ye cevap verebilirim.
Evet, Türkçe sorabilirsiniz. Kendinizi de tanıtırsanız sevinirim.
Ben yabancı misafirlerimizle biraz İngilizce konuşmuş.
Hoş geldiniz hocam ilk önce. I can speak English fluently, but if you...
Whichever you like, I can find it.
Okay, hocam bu paylaştığınız biyomedikal mühendisi yapıyorum ben. Biyomedikal mühendisi içerisinde sustain edebileceğimiz ya da nanopartikülleri daha çok hani sizlerin çalışmanız üzerinde bir uyumluluğu olan, bunu buradan hani selülozları sonuç organik madde olarak geçiyor, fakat hani çalışmalar arasında ne kadar bir uyumluluk sağladığı ya da nasıl bir işlemler sokulabildiği ya da hangi projelerde en çok yarar dokunabileceği hakkında bir öneri verebilir misiniz ya da bu hakkında çalışmanız var mı?
Tabii şöyle, bu nanoselülozun biyosensör uygulamaları konusunda bayağı yoğun çalışmalar var zaten şu an halihazırda. Bir de bahsettiğim gibi bakteriyel selüloz gerçekten çok dikkat çekiyor. Bunu uzun yıllardır Türkiye'de yapıyorlar yani. Ege Üniversitesi'nde olsun, Ülkeler veya Bartın'da olsun. Bunların Kore'de falan artık böyle yüz maskelerine falan kozmetik uygulamalarda kullanımları başladı. Artı yara örtüsü yapmak, işte yanık tedavisinde kullanılması gibi bir takım konular çalışılıyor. Onun dışında da daha farklı diğer selülozlar zaman çekti. Yani çok fazla bir şey, dokularda işte bu hücre iskeletleri falan bu tür şeylerle tişü enjinleri kullanılmaya çalışılıyor ama böyle çok makale bazında çok yapılan şey oldu, sanki söyleyeyim. Ama nihai böyle uygulamaya geçen pek fazla bir şey yok. Zaten mevcut PLA'lar 15-20 yıldır çalışılıyor. Ama bu bakteriyel selüloz kısmında çok konu var hala yapacak. Sen söyleyeyim, orada çok çeşitli bakteriler var, çok farklı maddelerle etkileşip, yani kompozitleri yapmak var gibi. Farklı mesela biz bir çalışma daha yapmıştık, burada koymadım da lise öğrencisiyle. Yapay damar yapmıştık. Zeytin çekirdeği atıklarından. Ona TPU ile birleştirdik. İçerisinde de bakteriyel selüloz, içerisinde pıhtılaşmayı engelleyecek bir şey kapladık. Üzerine bakteriyel selüloz kapladık. 2014'te Türkiye birincisi olduk lisede biyolojik yarışmasında. İşte o arkadaşlar bizden de çalışıyor. Film işte. Medikal sektörde İbrahim çok da severim. Benim master yaptım İbrahim. Yani bu bakteriyel selüloz söyleyeyim şu anda. Daha başka şeyler var da. Ben çok açık çalışmıyorum medikal. Kullanılan bir takım yerler okuyorum. Mesela ilk yarı daha yetkilerken şu an çalışmaya tekrar başlayacağız herhalde. Yeni mezun arkadaşlarla. Orada bazı şeyler olabilir.
Teşekkürler hocam, çok sağ olun.
Thank you so much for this very nice and nice talks. Very expensive for some extent, except for such a moment. And what is going to be in the future?
The reason I asked, I wrote the final conclusion, lignin containing CNF. It's not pure cellulose, or it has some lignin as well, but the price is much lower. Now the Turkish company is trying to promote it in the market, so I don't know its final price, what they are selling. To be honest with you, I just helped them for some research and to finalize the properties. But it's a little higher than, it's like $15–20 per kg at the moment, the price. But especially for some niche applications, it's very effective. But as you know, many things in technology need years, it will be dropping slowly. And even the carbon fiber is now getting cheaper and cheaper after 50–60 years now of advancement.
Yes, more question. Sorunuz var mı arkadaşlar?
Çok teşekkürler hocam. Pendik Üniversitesi'nden Şule Aytaş. Sunumunuz çok güzeldi. Biz de zaten Cem Hocam'la daha önce de çalışmıştık. Bu deniz makro alglerinden, deniz sosyallarından da elde edilen bu silozik yapılar var mı acaba?
Var, onunla ilgili makaleler yaptık aslında. Bir tane makro algler üzerine kitap bölümünde yayınladık. Hatta bir tane de deniz bölgesinden bir kompozit yaptık aslında. Böyle biraz yani curiosity tarzı böyle merakımızdan yaptığımız şeyler oldu. Yani ondan selüloz ekstrakt edenler var mutlaka. Özellikle bu sürüleri Ege Üniversitesi'nde de var, bizim Türkiye'de de var. O tür şeyler onlarla bir network halinde yapılabilir.
Güzel, çünkü kompozit çalışıyoruz. Değişik böyle kompozitler, doğal biyokompozitler. Çalışmanızın spektrumda onu görünce sonrası.
Onlar da var ama yani orada bayağı ciddi sürülebilirliği istiyor. Onu nasıl çıkartacaksınız? Mesela yosunlar gerçekten işte mikroalglerden biyoplastik yapma konusunda ben 10-12 yıldır geldiğimden beri bir şey yapsam diye düşünüyordum ama yeniden noktada epey ticarileşen ürünler başladı. Hani selüloz kısmı ayrı. Normal alglerden işte plastiklerden. Tabii bu bayağı hızlı gelişiyor şu anda. Yani ticarileşen boyutuna ilerledi. Ama dediğim gibi bunlar açık. Aslında şunu ben araştırmıştım. Hani dünyada ormanları konuşuyor herkes ama su altında 7.000 metrede, 10.000 metrede bir sürü acayip kaynaklar var. Hatta hocam Ege Üniversitesi 2020'de Teknopark'ta bir yer açmıştım. Filinya isminde. Bu Filinya isminde bir planktondan esinlenmiştim. Çünkü dünyadaki oksijen kaynağının %70'i planktonlardan geliyor aslında. Biz ağaç sanıyoruz ama esas yani o doğal ekosistemi sağlayan planktonlar. O planktonun bir tanesi de Filinya'ydı. Öyle bir güzel isim olsun dedim. Bir yıla yakın çalıştık Filinya'da. Epey bir firmaya proje yapıyorduk. Kendi koskoca projeleri vardı. Mail'e davet edilince şimdi karar verdik.
Teşekkürler hocam.
Question, soru? Özgür Hocam çok teşekkür ederim. Benim için de çok önemliydi. It is very important speech for me also because bionanocomposite materials is also my research topic. Cellulosic bionanocomposite materials on the biomedical engineering applications, especially on tissue engineering and the other applications of some production of scaffolds are my research area. Cellulosic materials and some materials from seaweeds are very important and very suitable for biomedical application. Yeah, especially cellulosic materials are biodegradable biopolymers. So it is very important, and maybe we can solve the problem of microplastic pollution in future by these biopolymeric materials. Is it future? In the future, is it possible? Do you think?
The thing is, as I gave an interview to our Turkish journalist, the thing is, we don't know how to deal with the waste stream. I mean, how to separate them, how to classify them. I also gave speeches to Karşıyaka Belediyesi, Çiğli Belediyesi, to local people as well. Even the municipality people, they don't know how to separate those things. The environmental engineers in those places. Yani çevre mühendisleri de bazen hocam belediyelerde yazına ayrılmıyorum. Yani ne gerek var? Hepsini karıştırıp beraber atalım falan. Yani biz daha önce atığı bir düzgün çalıştırırsak ki bu sadece değil, Hollanda'da, Almanya'da da benzer sorunlar var aslında. Günün sonunda ama tabii mikroplastik kan üzerinde çıkıyor şimdi.
Maalesef biyopolimerlerle ilgili bir Avrupa Birliği projesi gerçekleştirdik. Orada da aynı problemler yaşanıyor. Canlılarda da yüksek oranda birikmeye başladı. Ama bunların bir ürüne dönüştürülmesi de çok önemli. Özellikle kemik doku mühendisi, yapay damar yapımında da selülozik malzemeler, bu denizden elde eden malzemeler, üniversitemizde de gerçekleştirdiğimiz projelerde de yapıyoruz. Özellikle elektrik spinning metodu, 3 boyutlu büyü yazıcılarla bunların üretimiyle gelecekte çok iyi ürünler elde edilecek gibi duruyor. Sanırım bu seksiyonu tamamlayabiliriz ama hocam küçük bir hediyemiz var. Çok pahalı hocam. Bakteriyel selüloz biz üretiyoruz. Biz size verelim. O kompozitlerde onun içine bakteriyel selüloz koyabilirim. İkinci keynote speaker'ımızla devam edeceğiz. Now I am honored to introduce a second keynote speaker, Dr. Muhammed Reza Naymirat. Before he begins, I would like to share a brief biography of him. Dr. Naymirat is a material scientist and project manager specializing in polymers and fibers, particularly in melt spool fibers. He earned his PhD in textile engineering in 2016 from İsfahan University of Technology with research visit to Advanced Fiber Laboratory and the College of Textile at North Carolina State University. He later served as an assistant professor at Razi University and as a Theodor von Karman Research Fellow at Aachen University. Currently, Dr. is a research and development project manager in Sandnes Polymer Institution in the Netherlands, leading projects on biodegradable filaments, yarns, through the melt spinning. He is also Marie Curie Research Fellow, coordinating the PolyBioDeg project in collaboration with the University of Amsterdam, which focus on studying the structural properties of multiple bioplastics fibers on the correlation with their biodegradation behavior and mechanical performance. He is running various projects including Degratec, Biofood, liquid core fibers. Through his career, he has authored over the 45 journal papers, conference presentations, establishing himself as a recognized expert in fiber melt spinning, polymer sciences, and sustainable materials. He will be presenting his talk. Now I invite him to stage.
Hello, everybody. Ladies and gentlemen, thanks, first of all, to the committee for inviting me to this great conference. And I'm really a junior, even at our company. It's an honor and pleasure being here with seniors. Professor Yusuf Ujay, I met him, maybe he's not remembering, but in 2014 at IUTEX in Bursa. And thanks for the rector of this university. Thanks to Professor Cem, Professor Ali Demir, Dr. Mansour, and all of you for giving me time to present here my work. Sorry. Yes, I've been. And it's a great interest that here that this symposium has a nice and great contribution has a good reputation between the industrial companies in the whole Turkey as a national like consortium between them. Yeah, today I will talk about the effect of chemical structure of polymers. After the nice talk with Dr. Özgür, who talked about cellulose and cellulosic materials, nanocrystals, that most of them are not thermoplastic, but they are good in carbon footprint, they are mostly biodegradable, and all we know about Lenzing, which is a big company producing viscose yarns and filaments, and also staple fibers. Now we are going to dive into methspenic, thermoplastic polymers, and a great question by Professor Cem about microplastics. We are going to talk about thermoplastic fibers through fiber methspenic. Maybe can I have this remote microphone? Or... Yeah.
I can give this one. It's working. Good.
We are going to dive into melt-spun biodegradable fibers to study, to see the effect of chemical design and the processing parameters, and if the mechanical properties is important or biodegradation rate. We are going to see about the brief introduction about myself that's already given by Dr. Cem. I will go through introduction about SEMLIS polymer innovations. First of all, I need to describe what we are doing and how we are doing, what are our capabilities, and all you know about that, and then I go into the detailed scientific discussion with you about the topic. SEMLIS Polymer Innovations has it's a member of SEMLIS Group. SEMLIS Polymer Innovations, which is doing with the blue logo, doing R&D service to external companies, big holdings, universities, institutes, and so on, in different areas that I describe later. And our internal developments through SEMLIS Polymer Innovations is going to SEMLIS sustainable products. And what is our mission is solving the microplastics problem with developing biodegradable polymers and fibers, especially with fiber methspenic. How we do that, with SPI, we provide R&D service, solving polymer challenges for different companies, and also doing our subsidized projects for developing new products. That these products are going to SSP or SEMLIS sustainable products as an spin-off development. These developments can be done through subsidies from European subsidies like Horizon or JTF or national fundings and so on. But for developing a product, we always look into the market. What is the market size? Is it feasible to develop a biodegradable alternative or not? Our location is in Emmen, north of the Netherlands, close to the German border. A city named is Emmen. And Emmen is one of the main sites of AkzoNobel, was one of the main sites. Now DSM, Teijin, Morsinko, etc. is a good polymer consortium over there, a company is developing or polymerizing polyamine, another one is doing the compounding, another one is doing the recycling, or different activities. It's good to know that this K-Tech Park is known in Europe, and there are different sites, I think, in Switzerland, in the Netherlands, and Germany. And Sembis is also a member of Chemport Europe, and also a member of SUSPAC for Sustainable Polymers Consortium, etc. With other companies like Bio, BTX, and so on. Sembis, this new name is from 2017. After the first spin-off, which was monofilament for 3D printings, which sold out to BASF, and now BASF is making PLA is the 3D printing monofilament over there. It's a neighbor with us, but the development of this spin-off product was with API, which was the former name of Sembis. But our history is back to 1952, Alku. Alku was the first company in the world developing viscose fibers. Now, Lenzing has a big name, or Kelheim fibers, and so on. And afterwards, Alku invested in Nobel company from Sweden, and AkzoNobel was established. AkzoNobel had several production lines and also pilot lines. Still, the oldest pilot line in the world is our site, Sembis, which was developed in 1970, when Oerlikon was not born that time. And this is the oldest pilot line in the world, which is with us now. And different businesses in 2000 sold out to different companies, DSM, Teijin, or either the Kevlar and Tuaron was developed at the same time, and there is still argument that DuPont made the pararamide first or AkzoNobel made. Yeah. However, I'm going to our capabilities, how we do that, and what we do have to provide to our customers or to run our internal projects. We do have autoclaves, different autoclaves for polykondensation. We can make polyester, we can make PLA, we can make PBS, different copolymers, different ratios, etc. in gram scale, and afterwards to glass autoclave, which is 2 liters, and then 5 liters to 20 liters, and 200 liters. This is different scales for developing or designing, synthesizing new polymers. And after that, we can do solid-state polymerization to increase the IV of polykondensation polymers, polyamide or polyesters, to, for instance, the polyester from 0.64 to 0.85 or 1.02, etc. The scales are different: 10 gram, 1 to 3 kilogram, 60 kilogram, 80 kilogram, and 7 tons, available for our customers, which making us very flexible. We do have 2 screw extruders for compounding and blending of different polymers, from 500 gram up to 20, and even I would say if we work in higher RPM, even 50 kilogram per hour we can make. Melt spinning pilot lines are our strengths, which we have 3 different scales: 500 gram to 1 kilogram per hour, different filament numbers, different EPFs, 1 to 20 kilogram, which is through our bicomponent FET line, which is a versatile line I will describe later, and 20 to 40 kilograms through our Oerlikon pilot line for making technical yarns. We can make even monofilaments in 1 or even 8 numbers at the same time through our pilot lines. And we do have extensive laboratory for mechanical analysis, thermal analysis, and shrinkage, and UV stability, weathering, and biodegradation, the most important one. And we do have extensive polymer bonds, maybe more than 30 different types of PLAs, more than 25 types of PHAs, PBS, PBAT, and so on. We do have from commercial market. At least we have 20 kg of each, and we tested all of them. And we provide we provide routine protocol for recycled PET for butter, to fiber, for filter testing, and for polymerization of PHET from chemical recycling, startups, and big companies. As I mentioned, different scales. Sometimes they want to do SSP to go to technical yarn, sometimes they want to make yarn out of it, and so on, we do for them. Let's go narrow down to the topic, which is the microplastics. If we look at the market size of the plastics, last year in 2023, it was more than 450 million tons, which textile is only 15%, and packaging is almost half of that. If you look at this picture, it's more than 1 million tons every day. If you want to have better sense, 1 million tons is enough to fill Fenerbahçe Stadium full of plastic granules. This is the amount. And you need to consider that in textile sector, especially 110 million tons, which mostly is polyester, mostly is going to the landfill or shedding through microfibers, and most of them are ending up in the marine environment. If you look at this, the environmental impact of textile is very highlighted, especially in the Europe Parliament and Europe Commission. Different directives are coming out for to do R&D in this topic, or to ban some materials, or to replace polyester, etc. Water consumption in textile industry, we know that is very high. The carbon footprint is very high, 10%, but I have also another number from Textile Exchange, which is more than 4%. I don't know which one yet. We are not working on LCA, bio-based, etc. We are focused on biodegradable only. Yeah, and microfiber pollution, especially in the marine environments, textiles are the first one. Even in the normal environments, tires and tire debris are the first, but in the marine environment, textile fibers are the first, with 35% contribution in the microplastics in the marine environment. And there are some reports that every year, 500 tons microfibers and microplastics are going to the marine environment, and 7 million tons of plastics are in the oceans. Yeah. Okay, what to do? Our idea is to use biodegradable polymers. And if you look at the available biodegradable polymers, or you would say biopolymers, biopolymers can be divided to biodegradable, which can be bio-based, some part of them, or fuel-based and bio-based. But some polymers are in common. They are like PHAs or PLA, they are bio-based and biodegradable. These can provide a good platform to do R&D, to develop new products and alternative for the conventional products. Yeah. Then why melt spinning? Melt spinning is a clean process, fast, economic, and sustainable. Comparing to wet spinning, which is chemical wet process, and sometimes solvents, and sometimes not very good solvents, and so on. And then biodegradable thermoplastics and fibrous product can be an alternative. But we need to consider the glass transition, crystallization rate, and the comfort of the final material, final product, and so on. Yeah. If we want to consider all, we will end up with this big picture. Some parameters are coming from the nature of the polymer: melting point, TG, crystallization rate, crystallinity, and so on. These can determine the processing or melt spinning parameters, or spinability. At the same time, if we sum up with the processing parameters, we can result in different performance or properties for the filament yarn. And at the end, the environmental factors coming into account and making the biodegradation rate very complex. These are like, if you consider like this is like electric board, but if you follow, like the melting point can determine the processing temperature, or the crystallization rate can determine it, and then the tenacity of the yarn can be changed, then crystallinity of the yarn can determine the biodegradation rate, and so on and so on. The moisture level of the environment, the temperature, the enzymes, and so on. This was the reason that in parallel with the product development, we go to study these parameters as you see the title here, the structure of the filament yarns in correlation with the polymer design or polymer backbone, biopolymer backbone, processing parameters to end up in the mechanical properties and biodegradation rate of different yarns to study what is the effect of each. And this proposal was submitted to Europe Commission as a Marie Curie project after that I was started or hired by Centre Polymer Innovations when I was living in Aachen with Professor, doing research with Professor Gelees at ETH Aachen. I moved to the Netherlands to Sendis, and I started in September 2022. Then, at the same time, I applied for this funding, and then we got the funding to study these parameters to see if we can make yarns out of most of the biopolymers or not, what is the mechanical properties of this yarn, and how is the biodegradation rate, and how we can tune or modify that, and so on. We did all the trials through our FET machine. If you scan this, maybe you can get the link to see a video which is about in one of our processes. Yeah. We do have two extruders, different sizes, that is making us able to process 1 kilogram or even 500 gram per hour up to 20 kilogram per hour by choosing this one of these extruders. And the filament numbers can be between 1 up to 420 filaments. Quench height can be changed from 1 meter up to 4.5 meters. The gullets can be moved back and forward, and then water bath quench can come, and then we can make also monofilament. That means monocomponent, bicomponent, monofilament, multifilament, textile yarn, technical yarn, with the same machine. Yeah. We did more than, during my project, more than 30 trials to make different yarns from different polymers. That you see here, different DPFs, different speeds, but all of the trials with the 48 filaments and 400 micron spinnerets, the orifice size, and the winding speed differently according to the polymer, the melt strength, drawability, and so on, between 100 up to 2,500 meters per minute. Tenacity is different again based on the polymer, and elongation at break, and so on, and biodegradation as well. This is not the only work today on this topic, but maybe it's one of the last. But if you would like to see what has been done before that, we reviewed and summarized all of the works on melt-spun biodegradable fibers. More than 320, all summarized in one paper. You can just download and read about different groups at EMPA or Aachen or different institutes are also working on this topic. The mechanical performance of these yarns are showing that PLA still is the highest one, and is going close to polyester, but not the same yet. But the other biopolymers like PCL, PBS, PBAT, all they have some lackings. For instance, for PCL and PBS, elongation at break is very high. It's kind of like a stretchable yarn. And the tenacity of PLA good, and some other biopolymers also, And then these results are showing a limited number of biopolymers we could make yarn out of it. And the mechanical properties are limited for these biopolymers, or most of them. And some of them even they lose their tenacity during the time. Then what is the solution? Maybe designing a new polymer, maybe compounding of different biopolymers to modify them, and so on. That we will go into. Just this picture is showing the weathering or the results of tenacity after after 2 or 3 months of weathering at the room temperature. That you see PLA is keeping the properties very well, but some other biopolymers that we do have IP with, some institute, they are marine degradable, very high tenacity, but they lose their properties during the time. Then the service life is a big issue for biodegradable yarns, and we need to consider based on the application. We did also biodegradation through our BOD systems to study the biodegradation rate of polymers in powder level. This system is working based on measuring the pressure, and the pressure drop or delta P can be converted to biological oxygen demand. We did on powder level, less than 800 micron size, and 100 milligram of polymer. And these graphs are showing that PHAs are very fast in biodegradation, even in the marine environment, even faster than cellulose. The rest of biopolymers like PCl, PBS, etc. is slower than that. And another result is that marine water with sediment is more aggressive than only marine water. Do you know maybe someone? Why? The microorganism consortium in the sediment or the sands is more than the water. The bottom of the sea, but there is another problem there. If you go to the oceans, the temperature is very low. That's the reason that we are studying also the temperature in biodegradation rate. And we had also very nice collaboration with University of Amsterdam, Professor Gert-Jan Grutter, and we could use his setup for biodegradation in soil. 96 spots for putting the polymer powder in soil, and then studying directly the CO2 release, not oxygen demand. Oxygen demand is measuring how much oxygen your bacteria or the bacteria in the environment needs for the utilization, but here you are measuring directly the CO2 by capturing that in the KOH solution, and then 2 platines are measuring the conductivity of KOH solution. By changing that, it's automatically converted to the how much CO2 is released or captured. And what else? There are also other setups in different other institutes, like they work based on GC or IR methods for detection of CO2 directly. But this setup I was very happy working with. Very realistic and accurate data. Also, it's showing that in 1 year time, the accumulated CO2 we kept for all of the samples 275 milligram theoretical CO2. We calculated how much carbon we do have in the materials, and which we kept at 75 milligram, and then you see here PHAs faster than cellulose, almost 90%, cellulose a little bit less. PCl and PBS the same, after 1 year 72 almost, and PBAS and PBAT after that. PBAT, they claim it's soil degradable, the producers, but the results are not showing that. The NOVA Institute always is publishing that PBAT is soil degradable, but according to the chemical structure of the polymer, also because it has a benzene group, the terpentalic acid, it cannot be biodegradable very fast. It is biodegradable, but And we also differentiated between hydrolysis, abiotic hydrolysis, and enzymatic hydrolysis. If you put a polymer or fiber into only D2O or pure water, you will have only abiotic hydrolysis or non-enzymatic hydrolysis. But if you have enzymes and bacteria in the environment, it's also enzymatic hydrolysis coming into account. And the results show that different biopolymers can go through different pathways to the disintegration. Disintegration is the preliminary step for biodegradation. Disintegration or breaking up in the garden, etc., is not biodegradation. Biodegradation means you end up with the CO2 or CH4 with aerobic or anaerobic digestion. And the results are showing PBS has much more hydrolysis rate than PHAs. But the biodegradation analysis are showing PHA is the fastest one. This is showing that PHAs are going through enzymes for the biodegradation or utilization. But PBS, or I have also other titles that they go also with the non-enzymatic hydrolysis. Yeah. The dominant factor then for PHAs is the biotic hydrolysis. Let's go for the environments. Different environments we do have, and the different products can end up in different environments, and some of them are like, we don't have any solution for that. Like trimmer line, we cut the grass, and then the particles go to the grass, to the soil, and so on. Or the fiber sheddings in the washing machines, they go to the waste stream, and then the soil, and finally in the marine environment. Yeah. But industrial composting is the most aggressive one. Home composting is afterward. Soil, fresh water, marine water, and so on. We need to study biodegradation in these environments. For that, we made knitted fabrics from all the 30 yarns, the best one, with the socks knitting machine. We made these samples, and to go to study in simulated field test, not real field test, simulated field test, which name is mesotos. It's something between real environment and lab test. And it's good to know that this is disintegration, it's not biodegradation. Biodegradation, always we need to confirm with CO2 release. Yeah. A different environment, as you see here, compost, home compost, industrial compost, and 37. Which is the body temperature and sometimes used as accelerated biodegradation assessment. Water, wastewater, marine water, and sediment as well, soil, and also pure water to see only hydrolysis, abiotic hydrolysis. You see here that even PLAs, amorphous, semi-crystalline, and LD type or LL type, they have different disintegration rate. Here is at 58 degrees C. This is only one example, but we do have 500 pictures and different weeks from these samples, and it's still ongoing. And you see here, for instance, PLGA is much faster than all the PLAs. Maybe we will discuss the reason for that is by putting the comonomer, you are disrupting the arrangement of the polymer. Crystallinity is lower. The functional groups are more accessible, even for the water molecules or even for the bacteria. The biodegradation rate, disintegration rate is higher. And amorphous PLA is much faster than other POY or FTY. And LOY PLA is faster than POY and also FTY. Also, biodegradation assessment, I forgot to mention, in soil degradation, we also confirmed that LOY, biodegradation, here biodegradation rate, not only disintegration, LOY is much faster than POY, and POY is much faster than FTY because of the orientation and crystals. Yeah. Here is something that we... Also the field test. This is the application of muscle socks knitted with one of the yarns that we developed for muscle cultivation, for growing the muscles in the marine environment. They make a sock, we make a sock, they put the muscles and they put in the sea, and they want 6-month service life for the socks, and after 6 months, they don't want something remaining in the marine environment and so on. You would see that after 2 months, the disintegration at least is starting for these socks. Which this field test has been done in North Sea and still is ongoing. Yeah. Ongoing analysis for different environments, the weight reduction in the disintegration will be graphed, and the effect of microorganisms in different environments, fungi, and so on. And these mesopost studies will show if we are in the arrangement or confirmation with the biodegradation, lab biodegradation or not. Here is a full picture from the processability of different biopolymers, and polyester as a reference, and PLA, the first one, and other like PHAs and so on. You see polyester and PLA has very good processability, but PHAs and PBAT, etc. not. If you this colors here, polyester and PLA good, but the biodegradation rate of polyester and PLA not good. PHAs are good in biodegradation, but not good in processability. Even some of them, like PCl or PBS, are good in processability and biodegradation. They are not good in mechanical properties. And finally, hydrolysis as well. Some of them are good in hydrolysis stability, some not. And thermal stability as well, melting point and so on. You can see here clearly that we cannot have all these aspects in one polymer. Polyester is good in all, but biodegradation is not good. PLA is good, but it's only industrial compostable. PHAs are very good, bio-based, biodegradable, but processability is not good. This is making a contradiction between all aspects. As a conclusion, meltstone biodegradable fibers can be a good platform or alternative for conventional yarns as polyester and polyamide. Mechanical properties can be determined by crystallization and orientation, and biodegradation can be determined by disintegration, which can go through abiotic hydrolysis or enzymatic hydrolysis, and finally utilization. And this biodegradation rate can be in contradiction with mechanical properties, at least at a long time as a service life. And meeting all the aspects of mechanical properties and service life and biodegradation rate maybe is a challenge. And compounding or designing a new polymer, copolymer compound can provide a solution for tuning or these aspects for specific applications. And some publications from this study, as a review or research article or presentations, different conferences, including this one, which is the last one, and some products, marine degradable yarns and ropes, soil degradable trimmer line, bio-based biodegradable textiles, seaweed cultivation, mentioned about seaweed and also alga and so on, and compounds, home compostable compounds, soil degradable compounds, and these are some of the product spin-off developments that we are looking for marketing, scaling up, and at the end, I would like to thank the Europe Commission for monetary funding for this project, JTF for another project, which is the JTF Biotech project for designing a new polymer, which is ongoing now, and the University of Amsterdam for the collaboration, and also the committee of this conference for inviting me, and all of you for listening. If you have any questions or any remarks or any topic in mind, partnership, collaboration, and so on, just contact us. Polymerization, which this symposium is Lif, the Aliyaf polymer, which is fibers and polymers, and we have two divisions, fibers and polymers for polymeriization, which is very relevant. And thank you. If you have any questions, Saygılar.
Thank you, Professor. Thank you very much for your valuable speech. It is a very important topic for the future of the world, I think. Now, we will now proceed the question and answer session. Yes, we have a question. There you go. Özgürcan.
Thank you very much.
No problem. It's okay.
You can take, I have. So thank you very much. This is a very interesting area. This biodegradation is quite ambiguous field, as you know. There are a lot of different varieties of results published in the world as well. And I was curious if you ever worked with PEF fibers, because Avantium is trying to promote that fibers as bio-based, and I didn't see your list, right? And I think that's going to conflict me. And also, the second question, which type of PHA did you work? Which kind of copolymer? That's also another issue in the processing and other things that's highly critical. Thanks a lot for this fantastic presentation and very tedious and thorough. Thanks.
Thank you. Do you hear me?
Yeah.
Thanks for these two nice questions, very valuable. First, PF, interesting question. Avantium, we know them very well. Gertjan Fruter is the CTO of Avantium and full professor of the sustainable chemistry at University van Amsterdam. We know them very well. As I mentioned, we do R&D service for most of the companies around the world. But our focus, our main activity, or main direction is biodegradable polymers. We do like bio-based, but not as a single factor. Some polymers like PLA is bio-based and biodegradable. PEF, till now, there is no proof which is biodegradable, but it's one of the fully bio-based polymers. Different companies are working on that. Avantium is the first one, and they established the flagship for FDCA in the north of the Netherlands. They are making polymers now, some 100 kgs and tons. They make even yarns. We do this polymer. We did a lot of trials, but it's not our main focus for developing any products out of it. This is the LCA is very good, bio-based, but it's not biodegradable, at least. And the second question, PHAs, also very good question. I mentioned that we do have more than 25 types of PHAs. We can consider that P3HP and P4HP, these are two main homopolymers, and then you are going to P3HP, 4HP, PHPH, and so on. We do have all of these types, different molecular weights, even in powder P4 extrusion, even in pellet form, and some of them are very good, at least in extrusion and spin line, but problem in the gutters. And some of them even you don't have very good melt strength, and you can realize that which one can be very challenging. The more comonomer ratio, the more challenge, because it's going to be elastic, amorphous, and we do like crystalline and fast crystallizable polymers in the melt spinning. And then P3HP and P4HP is the main focus. Yeah. And I should add, thanks to Professor Jem, he had a very good biography about me, but I would like to add also, I had also industrial collaborations, and some of them, especially, about 2-3 years was with Turkish companies, Aydin Mensucat, Özçelik, etc. Then Türkçe'de biraz çok biliyorum. Türkçe konuşan, yani soru olursa cevap verebilirim hemen.
Ali Hocam, mikrofon.
O zaman Türkçe konuşacağız.
Tamam.
Muhammed Rıza, thank you very much for coming here and being with us. Çok teşekkür ediyoruz geldiğiniz için, bu sempozyuma katıldığınız için. Gerçekten bu biyobozulma konusu çok hayati bir konu. Bizim de akademik olarak çalıştığımız ve düşündüğümüz konulardan bir tanesi. Ben bu mezokozmi konusuna biraz şey yapayım. Yani onun hakkında biraz daha detay bilgi verebilir misiniz? Bu bir standart mı? Sizin dizayn ettiğiniz bir şey mi? Çok teşekkür ederim.
Sağ olun. Ben de teşekkür ederim davetinizden. İlk önce ettim yani. Mezokos test tam yani sertifikat almak için TÜV ve başka organizasyonlardan sertifikat biodegradation almak için bir tane şartlardan yani disintegration bir tane şartlardan ama tam şartı değil. Tam yani en önemlisi biodegradation o CO2 measurement. Yani %90 theoretical CO2'dan maddeden yani bakteriyle çıkacak ve ölçülecek. Mezokos biz yaptığımız iş ISO 20200 diye standart var. Biobeacon ve çok şeyde compost environment, home compost ve industrial compost. Biz onu biraz yaptık çünkü screen test yapıyoruz. Şu an sertifikat falan almayacağız. Ama onun için kumaş şeklinde ve ipliği çünkü biraz yapması zor, bozuluyor. Ölçmek, bilmiyorum tenasite ölçmesi veya gramaj ölçmesi biraz zor oluyor. Onun için kumaş şeklinde olursa daha uygun oluyor. Ve laboratuvar testinde tam field testi göstermiyor. Biz field teste geçmek için bu mezokos testi yapması gerekindeyiz. Ve sonra field teste bazen geçiyoruz. Yani bu bazı üniversitelerde veya enstitütlerde biodegradation setup olmayınca bu daha kolay olur. Yani daha kolay bir container, some additives, sonra kumaş veya monofilament ölçecek bir şey olacak. Yani ya tenasite ölçecek veya mass weight ölçülebilecek ve makros fotoğrafı visual inspection yani gösteriyor. En azından disintegration'ı gösteriyor. Disintegration olunca disintegration mandatory step for biodegradation. O olunca biodegradation'da mesela sen dimer veya monomere geçince hatta ki terpetalik asit kendi biodegradable bir monomer. Ama terpetalik asite polyesterde geçmek gerekiyor. Onu mesela enzimde yapıyorlar bilmiyorum. Glykoliziste yapıyorlar yani aynı şey ama CO2'ya veya CH4'a yetmiyor. Monomerde bitiyor. Umarım ki cevap verebilirim. Yok, test ettiğimiz yok. Sadece bir makine, çorap makinesi, knitting, sadece onu da renk, dop dyeing falan yapıyormuşlar ya. O makine o zaman andırıyor. Onu yani burada da belki firmalar yapıyor. Rengini bobinlerin veya üretimlerin arasında fark etmek diye o two-dimensional şey veriyor, vision veriyor. Onun için olabilir. Neden? Çünkü densiteyi falan biraz hatta ki aynı dokumada bir pattern, weaving pattern'da başkası fark olabilir. Ama tam şey değil. Yani iplik, ben söyledim, ipliğin orientation'ı ve kristalizasyonu fark veriyor. Ama en önemli şey olan polimerin structure'ı. O şey ana faktör. Sonra başkasıları geliyor. Mesela biodegradable olunca sen onu mesela bilmiyorum yavaş veya erken olsun diye onu değişebiliyorsun. Ama olmayınca hiçbir şey olmuyor. Hatta yaptığımız şeylerde bazı iplikler den yeri düşük ve den yeri yüksek olanı da vardı. Çünkü her ipliği aynı hızda yapamıyoruz. Ama sonuç tam tersini gösterdi. Yani kalın iplik olan mesela LOY sadece yapabildik. Ama kalın iplik geç disintegration olacaktı ama tam tersi oldu. Yani evet, yani PLA veya başkası PLGA daha kalın ipliğiydi ama disintegration daha erken oldu. Yani bu gösteriyor SSA var, Specific Surface Area, bir tane faktörlerden ama gösteriyor tam yani main faktör değil. Main faktör polymer structure, design. Sonra onun nasıl devrandığı su, abiyotik hidroliziste ve enzim ve bakterilerde nasıl onu mesela PHA ile hemen atıyorsun, 3 gün, 4 gün sonra CO2 veya VO2 grafı atıyor. Ama PLA'de hiçbir olmuyor. Ama PLA kendi biodegradable, ultimately 10 sene, 20 sene sonra hatta denizde de çözülebilir veya degrade de olabilir. Ama zaman, sertifikat almak için çok limited zamanda o sonuca gitmek gerekiyor. Yani PLA, Industrial Compostable 6 ay, Home Compostable 1 sene, Soil Degradable 2 sene, %90 en azı, sonra TÜV sertifikat veriyor. Bazen bizim produktlarımız TÜV sertifikatı var. Mesela Trimer'den şu an %85 falan oldu. Yani erken alacağız sertifikatı Trimer'den için. Yes?
Thank you so much. Very nice. On the other hand, some chemicals adding 1% to polyester and becomes biodegradable, and when compared with your result after they are playing after only 6 months, it is losing 60 or 70% of its mass. So it is really biodegradable. So do you think in the future polyester is going to be again a good option to continue with? If we install a bioresource, then glycol part can be produced from hydrocarbons, therefore another sources. Terbinaric acid one day should be. So if we install a viable sourcing of polyester, is it going to be the best choice still in the future, or we have to switch to other new ones, for example, PLA, PHA? It is compulsory for polyester to regain its importance again after being labeled as illegal.
Okay. Yeah, thanks, Dr. Mansour. It was a really nice question. I think this is also a question for us. You know, polyester, they are claiming by adding only 2% of master batch, which the master batch includes maybe 50%, 30, 20% of some additives, which are there. I know them as well, cycloadditives or primalogs or so on. But to my experience, yeah, they claim in losing the weight or disintegration, etc. First answer is that disintegration is not biodegradation. Maybe they are making even more microplastics, like oxo-additives, which is now banned in Europe. And oxo-additives, they were adding to the plastic bags, polyethylene, and then these can be, when they go to the like oxygen or water environments, they can break, and then the polyethylene can be disintegrated to many pieces. But if these micro-sized particles or plastics are not utilizable by bacteria, doesn't mean biodegradation. It means you are making more and more microplastics. I asked these companies, they showed me some graphs of CO2. I don't know, like 95% in 500 days in soil. Then I asked, why you don't have TÜV certificate? With this one, you can get TÜV certificate. Oh no, lots of, and I asked them, can you send me some master batch? They never sent. I don't know. But if they can make like the biodegradation rate, CO2 release, which needs disintegration, can happen more than 90%. Between 2 years, it's biodegradable. Then it's the first solution, I think, because you know, designing a new polymer, we always consider this huge number of facilities around the world that you cannot make another reactor, another process. You need to consider you should be able to make the same, like in Indorama, you just make a tree. Also, the Silas, I asked them, they told me that in the conference in Dornbirn, they told me just add the third monomer. It's not additive, it's copolymer. And everything is the same, it's the same. I told, if you add even 5% monomer, everything is not the same as polyester. even the same polyester is coming from the same company, IB is changing or something, it's not the same. The crystallinity would be the same, it would be different, and so on. But again, I asked them for a meeting and some samples, but it didn't happen. But I would like to test with our setups to see if the CO2 release or BOD is good. If it's going to be proven, then I think it's fantastic. Something, and they claim the tenacity is good, the service life is the same, everything is the same as polyester, but it's only when you finish your service and then you can put the landfill or soil, then it's not, to me, it's not really feasible.
Because the bias is claiming that it's biodegradable and it is final for CO2 from polyester using the ASTM 5511 assessment. And it proves that after 6 months it is completely or maybe more than 70% change in CO2. On the other hand, they say it's solid microplastic, but the estimate is only used for landfill, not for the marine environment. The mentioned those materials are disintegrated in the marine environment, but the polyester, I don't think is
between these environments, the most challenging one is the marine environment because the microorganism activity is very, very low. It's very low. Even pHA is showing in the sediment a little good biodegradation rate, in soil even faster, but in only marine water is very slow. And the second one, for getting the certificate, the time frame for the biodegradation, 90% is 6 months, at least with two. There is another institute in Germany, I think they accept for 12 months. 6 months, 90% in very low aggressive environment is very challenging.
Thank you. We have time limitation. Çok teşekkür ederim. Yabancı misafirlerimize Türkçe biliyor. O yüzden kapanışı şöyle Türkçe'de yapabilirim. Bu oturumumuzun da sonuna geldik. Sizi göndermeden önce birkaç hediyemiz olacak ama hemen kapatmadan önce değerli katkılarınız için bütün katılımcılara çok çok teşekkür ediyorum. Yani bugün Cuma hemen yemeğe geçip diğer seksiyonu da yetişmemiz lazım. Çok teşekkür ederim.
Ben de teşekkür ederim.
Değerli katılımcılar, sempozyumun ilk oturumu sona ermiştir. Saat 14.00'a kadar öğle arası ve poster ziyaretleri için ara verilecektir. 14.00 itibariyle E blok konferans salonu ve E blok 64'te oturumlar devam edecektir.
Yes.
Şu an evet. Değerli katılımcılar, sempozyumun öğleden sonraki oturumları başlıyor. Oturum 101'i gerçekleştirmek üzere oturum başkanı doçent doktor Haşim Özgür Tabakoğlu hocamıza kürsüye arz ederim.
Good afternoon, everyone. Welcome to our symposium. In this session about fiber and polymer advancement at the International Fiber and Polymer Conference, we will explore some groundbreaking work that pushed the boundaries of material science and contributes to applications that impact various sectors. So, I'm sure each speaker will bring a unique presentations and from foundational research and cutting-edge applications. So as we go move through presentations, I encourage you to think critically and engage with the presenters and consider how these findings connect to the broader advancements in this field. So after each presentation, we will have a short question and answers session. So please hold your question until the end of each talk, and I look forward to your dynamic discussions ahead. And the first presenter, I'd like to introduce you from Istanbul Technical University. He's currently also managed the TEMA labs at ITU, established in, I think, 2003 and based on the Gümüşlük campus. The studies are concentrated on interdisciplinary field of engineering fabrics and design and manufacture of specialty instruments for each material. So, focusing on these novel fiber applications, TEMAC facilities are divided as filtration, separation, composites, and biomedical laboratories. So the research is funded, I think, more than 10 international and national institutions and plus companies. TEMAC supports more than maybe 30 graduate students and is an authority in this research of fibers in Turkey. The center also houses state-of-art facilities for product development and analytical services, plus material testing, analysis, and evaluation. So I'd like to welcome Professor Ali Kılıç.
Okay, good afternoon. Today I'm going to talk about some history of TEMAC Lab and also our capabilities that we already developed, the equipments we have developed, and we will discuss about them. With this presentation, actually, we want to enlarge our collaboration with our friends, with our partners. So far, we hosted many companies, many colleagues actually around the world to try and see our equipment's capabilities actually. In this regards, I like a word of military actually. When we try to form TEMAC actually, reform TEMAC, we talk about the word in military, a victory is looking for 4 things. One of them is strategy, one of them is tactic, also motivation, and finally finance actually. These four things are kind of must for us to proceed, for us to produce something. So strategically, Thermaglab actually, we position Thermaglab to produce people's things and the machinery, the equipment, how to develop the equipment for fiber things. And hopefully, we want to become one of the authorities actually in fiber research and fiber investigations. So for that reason, I warmly welcome you to visit our facilities, our place also. We will be more than happy to host you as well. So in Thermaglab, we want to produce fibers for different purposes. So they are after the textile production, especially for the technical textile things, we can concentrate on energy materials, composite materials, filtration and separation products, and biomedical uses. So today I'm going to talk about the instruments that we developed for that purpose actually. I just wanted to make such a classification. We do have nanofibers and fibers. We developed some equipment for nanofibers especially. These are really popular materials and kind of easy to establish in many different laboratories. So electrospinning is one of them. In my lab in Thermaglab actually, I was just a master student at that time in 2004. We started these machines for electrospinning. And after that, maybe we gave a break, kind of break, and we checked for aerospinning, centrifugal spinning, and e-aerospinning by 2019, my friends. On the same hand, actually, we need also equipment for the fibers as well. Fibers, I mean, these are real fibers, let me say, but nanofibers also found themselves in many different applications. So the thing is, for microfiber production, for real usable fiber production, I mean, in textile use, we produced wet spinning equipment, matte spinning equipment, a matte blowing device. So these are just, process instruments actually to form some polymeric structures into fibers and nanofibers. And lastly, we concentrated on actually something more novel, I can say, dry jet wet spinning and gel spinning procedures. So these are just, maybe I gave these times, but the times are just the very first fibers we were able to obtain actually from the equipment we were able to design, my friends. So how it started actually, it started with the nanofibers. So we collaborated with Boeing company. So they asked us kind of filters for the aircraft cabins. So at that time, the question was to produce kind of, modified fibrous photocatalytic filter media for the requirements in the aircrafts. There are some gases actually that are somehow stored in the aircraft environment, and these are some kind of, difficult to remove gases. We need to use activated carbon, which should be replaced very frequently. So for that reason, they asked us how we can go for this photocatalytic filter media, and we recommended them that we can produce some electrospoon media, and these media can somehow modify with titanium dioxide layers or zinc oxide layers. So these photocatalytic structures are going to cause kind of degradation of these gases, my friends. But later on, the question appeared when they see the electrospinning mechanism, they criticized us harshly actually. So the speed of the productivity of electrospinning was kind of low. So as you see here, I got some average values here, 1 milliliter per hour speed for some polymers that has very low concentration actually. So they ask us to go for some new techniques that we can improve our capabilities, and we can provide them real filter media that can be usable in aircrafts. So later on, we said that rather than use of electrostatic forces, would it be possible to make it with compressed air? So if we form a kind of coaxial nozzle at some angles here, as you see, we can somehow blow the fibers actually. This is kind of maybe a novel technique compared to matte blowing, which is widely known in non-wood industry. In the same time, also we concentrated one different equipment, one different system which is very much like by the kids actually, this cutting candy mechanism we call it. So would it be possible to produce fibers using centrifugal forces? Same as the, candy, same as the sugar things here. If we put polymer solution, this polymer solution can form fibers. And even we can go nanofibers. The question appeared here is, for the case of polymeric fibers, we have to go very, very large RPM levels. The rotation should be very high. And even after rotations at 10,000 RPM, we can reach similar fibers of similar diameters as you see here. One advantage of solution blowing and centrifugal spinning appeared to us after working on these mechanisms that we can, as we are utilizing from some kind of mechanical forces, we can increase the solution concentration as well. Please keep this in mind, my friends, that if we are producing our polymeric materials using some sort of solutions, we have to have the highest concentration possible. Otherwise, your productivity is going to get low. So this is one ambition actually we do have, that if we increase the solution concentration up to maximum values like 20-30% concentrations, our productivity is going to be getting larger. So this go with some kind of equipment actually, solution blowing, we call it aerospinner, and I am happy that many people nowadays are using, rather than solution blowing, they are also calling this system as aerospinning. So we manufactured both units, and we were able to make both large-scale equipment and roll-to-roll systems to produce nanofibers, my friends. We somehow acted really professionally. I was happy, I was maybe lucky that I had some friends to help me through this simulation things, and also the automation actually. These two parts were really critical. So we checked for the, air flow rate versus fiber formation. As you see here that in some regions of the nozzle, actually, we can increase the this flow rate, air flow rate up to 600 meters per second. So these are really high values. And we are just trying to process something which is like, I can say, millimeter, even micrometer scale. So for that reason, we should be really careful. We should somehow act really gently to form these polymer solutions into nanofibers. So we spent quite a lot of time actually for this, nozzle actually, the solution blowing nozzle. After seeing that, after reaching such high speeds, my friends, we were able to design the nozzles for this big scale production. Here you see the productivity of the equipment. It is just blowing the fibers towards a collector, and this collector is, there is a kind of non-woven media that these fibers are somehow collected on that. So the good thing with the equipment is also something that the system is independent from electrical properties of spinning solution. If you are going for electrostatic spinning, you have to consider the conductivity, you have to consider the dielectric properties. But here, as we are using the just the compressed air, the system is not dependent on the electrical properties, so you don't need to put, some kind of salts into polymer spinning solutions that you don't want. Imagine you are producing something for biomedical applications, and you have to put some ions and salts into your solution. And this is also independent from the environment, especially in the electrospinning system. You may need to reduce the relative humidity in the environment down to 20-25%. So the system is quite harsh, I can say, in this regard. But we observed something interesting. When we go for solution blowing, the fibers are okay, very high speeds. We were able to increase the productivity from 1 milliliter per hour speed to 100 milliliter per hour speed. But the question comes that at these very, very high speeds, the air, the polymer jet can somehow integrate into itself. So it forms these fiber bundles. So we were able to find an answer for this question, my friends. We are not using very high potentials, very high voltages. It's, I mean, like 20 kV, maximum 30 kilowatt potentials. We were able to develop also one other mechanism which we call electroblowing. So electroblowing is a hybrid system that you can, we have two benefits actually. One of them is the fibers are becoming more, I mean, they can disintegrate actually. And one other advantage is it's produced at very high productivity. Imagine that you have these compressed air forces plus electrostatic forces. So such a hybrid system, my friends. After seeing that actually, after some collaborating with some other groups actually in medicine especially, we found a nice toy actually. I love this toy. It appeared like maybe 2 years ago. This is a portable nanofiber production system. It is the easiest mechanism, I can guarantee you. Because you don't need a power supply, you just need a compressed air source and Aragas, I mean the nozzles you are able to manufacture. The purpose of this device actually in our, I mean, laboratory was to make a portable system. I mean, this was going to give opportunity for the medical doctors that they can easily put the medicals onto the wound. And I mean, imagine they're gonna mix the, I mean, medication, I mean, the drug and the polymer solution, and they can directly apply it onto wound area, my friends. So it is an exciting instrument actually. I have a video here, so this video shows that a kind of nanofiber coating on the head. I mean, it is somehow faster, accelerated video, but believe me, it is really fast. It is really fast mechanism. I mean, in 3 minutes you can cover your hand without the requirement of electrostatics. I mean, this is the good thing. So some groups in, I believe, Israel and the United States also work on that, but they utilize from electrostatic level. So imagine that you have 30 kV potential over your hand. It is kind of not acceptable for many patients, and it can easily form also sparks. So you see here that my friend's hand is completely covered with monofibrous structures. Anyway. So this system is portable. As I told you, one other mechanism, I mean, one other force in the nature we can utilize from the centrifugal forces. I mean, we just simulate this actually cotton candy mechanism, but we saw that we need to go very high RPMs here. So we do have kind of, I mean, something after you can think that, oh, this is a simple thing they did. But it is really maybe minor, but it really took a lot of time to develop these nozzles, my friends. So using these nozzles, we were able to coat them somehow on these collectors, my friends. These are vacuum collectors, by the way. I mean, nanofibers are going everywhere, so we are just trying to take them onto this collector, my friends. So this system can rotate at up to speeds of 15,000 RPM. It means that 250 rotations every second, my friends, you can imagine. So one of the crazy things we made with this equipment is it just stops when you open the door, actually. My friends stop the safety buttons, actually. It can stop in just 2 seconds. I mean, in 2 seconds, even at speed of 15,000 RPM, it directly stops. I had a video of it, but I did not put it here. So we were able to form fibers using centrifugal spinning also. I can say that in the lab right now we do have 3 more mechanisms. After electrospinning, we do have 3 more mechanisms to form the nanofibers. And to be honest, my current research is just on this thing. So nanofibers, somehow people criticized what the hell they are going to be used for. So the question was really rude maybe for us, but later on during the COVID conditions, my friends, we probably saw that nanofibers become one of the most popular fibers. So the thing is, I was called by maybe hundreds of people every day that they were asking me nanofibers to put into their face masks. For the aerosol filtration, after this filtration project with Boeing company, we concentrated on finding some solutions for the COVID-19. Filtration is a crazy topic actually. Nowadays in our developed states, we do have this problem, air pollution. You probably feel also there happens many deaths for that reason, especially pandemics. You know, we remember from COVID, but probably in the next decade we are going to have more pandemics actually. So the frequency of those pandemics are increasing after the globalization of the world. We are going to see that more and more actually. And there are also some requirements in the hospitals, operational rules. For that reason, for aerosol filtration, we have to find an answer. So again, the question right now, when I'm explaining the solution lowering and centrifugal spinning, I asked you to think about something that I was able to increase the polymer concentration up to 20%. But would it be possible to make 25%? Would it be possible to make 50%? Would it be possible to make it 100% concentration? Which means that melt blowing, we do have that melt blowing. So during the time of pandemic, actually, as we are asked for this math-based fiber production things, we formed such an equipment also. We do have our own melt blowing, small-scale melt blowing system. By the way, this is a 30 centimeter width mechanism, so it's not for producing the face masks, my friends. Later on, a question came to my mind. I mean, would it be possible? Okay, we do have this 30 centimeter width die, but would it be possible to make it with just single one nozzle, my dear friends? It is like just same as the regular air spinner we were producing. As you see here, I do have just a nozzle here, and this nozzle is just, you know, blowing the fibers, mostly microfibers, I can say, towards the collector area. And I am happy to share this equipment. This is one equipment we were able to finalize last summer, my friends. As you see the fiber formation, we can easily make it here. We used for something used for blood filtration. This is polybutene therapy. As you see, even for this case, the equipment is working quite nice, and I'm happy that the webs are relatively uniform. Actually, this is something good also. So this melt blowing gave us the opportunity that we were able to make 100% polymer processing, meaning that we are not spending time for the preparation of the polymer solutions. Directly we can go melt blowing. So this is so this is also asked by many friends who are working on biomedicals actually, because in biomedical products, the use of the toxic solvents is kind of crazy. Melt blowing does not require any solvent. So the question here is, right now actually in my mind is, would it be possible to produce thermoplastic fibers, meaning that from the mass? There are some constraints and there are some advantages actually. So these are some constraints that people do not spend time, but there are really plenty of advantages of these mechanisms. So these are some works we did for the nanofiber and mat production, my friends. We do have also fiber spinning equipments. This is one of the equipments we are producing for fiber processing. These are in our lab. We can try for different polymers. We can go up to, I believe, it is like POY scale. I mean, partially oriented yarn. We were able to spin with this equipment. The question also comes when if you have melting, I mean thermoplastic polymer, the question is how we can optimize it, how we can add some functionalities to such thermoplastic polymers. So for such studies, my friends, we are in need of twin sleeve extruders. The previous speakers also talk about the mechanism. So this twin sleeve extruder gives us capability to go for polymer mixtures. We call them polymer blends, polymer and additive mixtures actually. So derivatives can be first produced using the compounders, and after that we can go mass spinning. So we do have our lab scale compounders also. So here you see that there's a graphene maybe PVDF mixture here. So where components can be used even for the purpose of polypropylene mixtures. And also we just connected it to a film casting mechanism. So this compounder can be used for both compound master batch production, plus we can also cast polymeric films for the use. I mean, you can ask me the question, you were supposed to become a fiber authority. What is the reason behind films? But we split fibers, maybe you heard the term. What they are doing is they are just splitting these films into fibers. These are also some kind of, they also find use in industry. I mean, firstly you are producing the films, and then after you are just splitting them into fibers. Okay, so after such studies, actually, I mean, electrospinning I talk about centrifugal spinning and solution blowing, electro-blowing systems. So the main difference between these mechanisms from the aspect of biology, my friends, is the shear rate. I mean, in electrospinning, I can say that you are applying a very low shear rate. This is the reason, actually, why we do not have high conductivity, high productivity. In the case of centrifugal spinning, you are maybe twofold, I mean, logarithmically, it's like 100 times higher shear rate. I don't remember the exact rate. And one step ahead, we do have solution blowing, actually. I mean, in the solution blowing process, you are applying the highest shear rates. This is one of the reasons behind productivity, as I said. So the second question comes to me, I mean, as a polymer guy, as a fiber guy, as a fiber engineer, let me say, it is a better term for myself. So in the mass spinning case, we are applying very, very high shear rates, because nowadays we can go the drawings up to 10,000 meters per minute. So these are really high values. So the question is, basically the difference between that is, in the wet spinning process, we can do it at very, very low speeds. I mean, in the case of cellulose, as far as I remember, we are using a speed of 40 meters per minute. So you can see that we are applying a very low shear rate to the fiber. So for the case of researchers, I mean, I just want to say that if you have something that is not mass spinnable, maybe there is a room to make it wet spinnable. Or even we can go for dry jet wet spinning. So we do have these two equipments. So for low, actually for, I mean, small spaces, we do have in the lab also. I mean, there is a spin pump here, so this pump is just transferring the polymer solution into kind of coagulation bath. After that, there is some drying, there is washing things, and contact drying, and you are winding. So this system is actually more or less the same, but it is more applicable for the pilot studies, and it is more applicable for the high viscosity dopes. Remember that in the beginning of my presentation, I told that we have to increase the solution as much as possible. So we have to increase the viscosity to very high values. Also, there is some room also to work there. There is plenty of room actually for the gas spinning. Imagine we are trying to produce some ballistic fibers like Dyneema, like Kevlar. The liquid crystal structure and actually the structure of these solutions causes very high viscosities. So these very high viscosity solutions cannot be produced by small pumps. Instead, we need kind of specialized gear pumps. So my presentation was full of some videos. Here you can see another video also. I mean, polymer is pumped towards here, and the coagulation mode, fiber formation. By the way, I mean, at the beginning of the day, I was thinking, as you see, the fiber is coming from here, so it is washed here. After 2 stages of washes, we can collect them on the binder. And it goes to kind of drying actually here, and after that binding. The question, my friends, is there is a challenge actually, another challenge. As you see, we are using something bad, something polymer solution. So low productivity. It is something good for my research. I just want to produce the fibers. But the question comes here is that the liquids used over there, even the coagulation bed itself, and plus the solvents that are used for the polymer solution, we have to recover them. I mean, right nowadays there are really big and complicated recovery systems that you can regain and you can reuse the polymer solvents or coagulation bed, the chemicals used over there, that's up to 99%, even some systems can find 99.5 recovery rate. So this is something good, and this is actually something keeping wet spinning still alive actually. I mean, in normal thinking, imagine that there is a mass spinning process, it go very high values. On the other side, I have something working at a scale of 40 meters per minute speed. It's very low, but as soon as we recover the coagulation bed, as soon as we recover the solvent, the systems are quite environmentally true. So this is, we watch it. TEMAC is not only a laboratory for such equipment. I mean, I'm happy that we do have many partners, especially from the mechanical engineering departments, especially from medicine. They help me a lot. So we have these such social things. Actually, TEMAC is one place that ULPAS, the first ULPASs took place. I will be happy to host my friends here in Istanbul as well. And there is something, an opportunity maybe for my friends here, especially for master and PhD students, even undergrads actually. So we want to organize these summer schools somehow in the summertime. We will be happy to host our friends in TEMAC as well. So these are some list of our partners actually. I mean, I'm saying that partners, we are still in touch, we are still working together. So this machinery actually made us kind of a little bit, maybe I can say, famous in the world. And right now we are still we still continue our collaboration with our partners. And luckily, you know, for some material actually, I need to say that, I mean, MIT professors, let me say, they were not able to produce. I mean, we produced at that time kind of silica fibers. So these silica fibers, at that time, they asked us to produce these silica fibers for them, and we sent them. We actually sold them at that time. It was also good to have MIT in our portfolio. Thank you very much for your attention. I am sorry if I said something crazy. And I again want to invite all my friends, if we come together, we're gonna be stronger, we're gonna work together, we're gonna make it better. Thank you.
Thank you, Yıkılış Hocam. Really, TEMAC is doing very good things, very good projects, and congratulations for these projects for you. Yes, this is now question and answer session. Do you have any questions, Professor Ali?
Presentation was so clear.
Yes.
Thanks a lot. It was very interesting, and I'm happy that we are working with you. My question is that between your melt blower, which produces nanofibers, and normal melt blowing style that the people producing in the industry for not nanofibers, what is the main difference? Is it the nozzle structure or the air pressure or anything else?
I mean, in the industry, the melt blowers, regular melt blowers, are generally producing fibers of 2 to 5 micrometers. In our case, we want to lower these values down to 0.5 micrometers. So for that reason, actually, we have these nozzle structures. Of course, it is not only system-based parameter. I mean, In our cases, every time we have this triangle. One of them is system-based parameters, one of them is process-based parameters, and material-based parameters. So we found this equipment, and right now we are doing our trials to reduce the fiber diameter directly from these mechanisms. And in the regular systems are just, people are happy to go these microfibers, let me say. And we are going to reduce the channel diameters down to 0.1 micrometer. If we can achieve that, I believe we will be very close to nanofiber scale. I hope so. I hope I was able to answer. Yes, sir.
Thank you, Ali. It was a great presentation, very successful developments. I have one question. What is your business plan? Like, are you thinking about only selling these pilot lines to the universities, or no to companies, or no just doing R&D for companies, or are you thinking about scale up, like making bigger machineries for metal spinning? What is your plan for the future?
Actually, I forgot to tell you that when I come to Turkey, my hometown, I did not have collaborators in Europe. It was kind of a problem for me because we had the ambition to go for some European Union Horizon projects. Even I stayed in UK for a couple of months. I've been to France, I've been to Germany, but the persons I got in touch were they were really rich, and they did not have such an ambition to write a project proposal. So what I did, my friend, is we just made this solution blowing at that time. I just put this on YouTube because I was not traveling very frequently. And after that, I started to check the names from Europe, from France, from Spain, from wherever. And I was sending them email showing the link of the equipment, actually. I mean, we developed an equipment which is solution blowing. It is very nice. We made a mat blowing. It is very nice. Please collaborate with us. We are going to go such a project. Later on, what happened is someone from Hong Kong emailed me. He said that we love the equipment. It is very high productivity. It is good. I said, okay, but Hong Kong is very far away from us, so I cannot sell it. So I cannot collaborate with you, sorry. And the guy told me that we don't want to collaborate with you. We want the equipment from you. And this was the actually very first, success we were able to make. I mean, I was trying to collaborate with people. They just asked me the machine. Okay, give me the machine and go. So the question, after that, Areka became a company. The Tamak actually, Tamak and its spin of Areka became working parallel. And right now, nowadays, we are giving them machines, actually, these machines. And somehow, Tamak is funding its research from Areka's resources. It is just connected like that. Probably in the future, we want to dive into more material side. I don't want to spend too much time with the machines because machine development is kind of crazy, kind of difficult compared to material research. Right now, I just want to say that we do have almost all the fiber spinning equipment. We don't have dry spinning equipment and flash spinning equipment. These two we don't have. And I don't want to work on these two mechanisms. My ambition nowadays is just produce the best materials using these instruments and collaborating with my friends on material production, not machine production.
Product development.
Exactly. Thank you. Good success.
Thank you very much. I've been following you on LinkedIn. You have wonderful equipment in your lab. It's really inspiring, fascinating for us. So are you working on any medical sutures, these kind of medical fibers in your group? Or?
Actually, these mini wet spinners came to the lab last summer, Hojam. And if it will be, probably we are planning. It requires wet spinning procedure to go for absorbable sutures. We have the equipment right now. We will start hopefully in the coming years. I will be happy to collaborate with you also on this topic. Thank you very much for your attention, my friends. Thank you.
We'll jump to second presentation. The topic is the development of PLGA nanofibers enhanced with curcumin silver nanoparticles, and this will be presented by Cansu Güneş. She's from Çelebi University, and she's a PhD student there. And she's a lecturer at the University as well, in the İzmir Vocational School in Biomedical Equipment Technology Department. And she has studies related with using electrospun nanofibers as biomaterials, and especially focusing on wound dressings. So I'm inviting, okay, Cansu.
Hello, dear visitors and Bollywood colleges. I'm Cansu, as Session Chairman as mentioned. And now I will present you our latest research conducted with Fatma Sen, Mustafa Mert, and Professor Ahmet. In this study, we focused on the developing PLGA nanofibers enhanced with curcumin, encapsulated with silver nanoparticles. I will start with the objectives of study. As most of you, wound dressings aim to prevent severe infection, promote wound healing, and minimize scar tissue formation. All these aims serve as enhancing patient compliance. When we consider about nanofibers properties, nanofibers, as you know, have high surface to volume ratio and the porous network. Due to these properties, we meet the criteria of wound requirements in terms of increasing the absorption of wound fluid, in terms of keeping the damaged area moist by retaining water vapor in the wound environment, and in terms of allowing the wound to breathe thanks to oxygen permeability due to nanofibers' porous structure. And in this research, we applied electrospinning technique to manufacture PLGA nanofibers doped with green synthesized silver nanoparticles with curcumin extract. As you know, silver nanoparticles known with its antibacterial, antifungal, antiviral properties. And for this reason, it is applied mostly in biomedical field, but its synthesis methods, mostly using flammable and hypotoxic chemicals. Instead of using toxic chemicals, we can apply the green synthesis method. Instead of using chemicals, we can use biomolecules, microorganisms, to produce safe and environmentally friendly particles. For this reason, we selected the curcumin in Turkish zerdeçal because of its antioxidant, anti-inflammatory, anti-tumor, and antibacterial properties by synthesizing silver nanoparticles. And as a nanofiber, we select PLGA nanofibers due to its biodegradability, biocompatibility, and favorable mechanical properties. And it's suitable for wound dressings because of it meets their mechanical properties. The experimental procedure consists of two stages. First stage is the green synthesizes. While preparing curcumin extract, we use distilled water with curcumin powder, and on the other hand, we prepared the silver nitrate solution together with the distilled water again. And to synthesizing stage, we dropped the silver nitrate into the curcumin extract drop by drop as a 1 milliliter volume, and then we waited it 24 hours for the reaction. After that, the reaction we vaporizate in oven at 200 centigrade degrees, and then we added these nanoparticles into the PLGA solution using the chloromethan and dimethyl formula with solvent before the electrospinning procedure. After preparing electrospinning solution, we use this solution in a high voltage electrical field to form thinner nanofibers. I want to pass to the result and discussion part. We analyze these nanoparticles with TEM, transmission electron microscope. We found that the synthesized silver nanoparticles was found to be between 7 and 72 nanometer with the mean diameter of 13 nanometer. And when we conducted with the EGS spectrum, we catch the silver peaks at 3 kilo electrovolt in EGS spectrum, and it shows us the production was successful. And we also investigated nanofibers with scanning electron microscope, and we found that the produced particles local PLG nanofiber diameter measured as about 220 nanometer. And in FGIR part, we showed the curves. The red line is a PLJ and the blue one is a, the black one is PLJ and the red line was symbolized silver nanoparticles of PLJ. And the FTIR graph shows us silver nanoparticles addition doesn't change any chemical structure of PLGA. And about antibacterial activity, we showed a surprising result due to the produced silver nanoparticles encapsulated with curcumin in PLG showed more effective inhibition zone diameter in Staph aureus bacteria. This zone inhibition diameter was lower in Escherichia coli according to Staph aureus. And we also conducted this biopolymer in biodegradation test. According to test results, the silver nanoparticles of the PLG nanofibers showed less degradation rate while we compare it with its PLGA. We conclude that the addition of silver nanoparticles increases impregnation resistance and prolongs the degradation time. It's concluded that more controlled delivery, we can say that more controlled delivery we obtained. As a conclusion, the spherical shaped silver nanoparticles encapsulated with curcumin with an average diameter of 13 nanometer were produced by the green synthesized method successfully. And SEM analysis revealed that silver nanoparticles cause rawness in the fiber diameter. The rawness is also may prevent the bacterial infection, the rawness. And chemical components of PLGA didn't change, so the PLGA continue its stable structure, which is confirmed by FDIR analysis. And the Staphylococcus was the bacteria in which nanofibers showed the most bacterial effect compared to Escherichia coli. The PLGA nanofiber sample degrades rapidly, while the silver nanoparticles doped PLGA nanofiber sample degrades slowly. The addition of silver nanoparticles increases impregnation resistance. We can say that at the end of this study. In future, we considering about the enhancing antibacterial effect in PLGA nanofibers using the synergetic effect of drugs and silver nanoparticles together, and also we would like to test the antibacterial effect of drug and silver nanoparticles to compare. This is the end of the presentation. Thank you for listening, and sorry if I have any mistake.
Thank you for your nice talk. Yes, now you can ask your questions if you have.
Thank you, Cansu. It was a very nice presentation. I have just to clarify, maybe I missed it. First is that the PLGA, from which company was the PLGA that you used, and do you know about the co-monomer ratio or not? And the second question, maybe, do you know why silver is postponing the biodegradation rate? Is slower? Why?
Okay.
Maybe I can answer if you don't know, but I will answer later.
I want to begin with the first question. The PLGA, which I used in that study, molar ratio is 75% PGA to 24% of PLA. It is the molar ratio. And in that graph you mentioned, the biodegradation rate is more slowly in silver nanoparticles of PLG. I think about now, the reason was maybe the silver nanoparticles of PLG make more electroconductive and so make in electrospinning process it makes more firm bond. I think it's made difficult to
disintegrate or
yes.
Or maybe the antibacterial effect of silver is happening there, and then bacterial activity is less because of the silver, maybe. Yeah. But it was very nice. Thank you.
Thank you. Okay, if you have any questions, I can ask you in Turkish or English. Doesn't matter.
One more question, I think.
Thank you for your nice presentation. I'm Çolpan Kandineş from Bakırçay University. I have two small questions. Maybe I missed. I'm not sure. Did you characterize the nanofibrous mats to demonstrate your nanoparticles, such as EDX or mapping analysis? I just saw the EDX, SEM analysis, SEM images. This was the first one. And the second question was about the releasing study. Did you do any releasing study? Thank you.
Okay, the first question, I want to begin with the first question. We carried out the TEM image for silver nanoparticle synthesized. This is the image. This is the image of TEM, and you can see the nanoparticles as dark regions of image. And in biodegradation, we couldn't investigate the nanoparticles separately. We all investigate in biodegradation test, all together nanofibers added with silver nanoparticles. And you can see in EDS analysis the silver peaks at 3 kiloelectron volt. This shows the existence of silver in nanoparticles, synthesized nanoparticles. If you have any question, yes.
Cansu, thank you very much for this nice piece of work. This is very exciting to see this silver nanoparticles under TEM. They are clearly spherical particles. I wonder if they are agglomerated or they are all separate like this. It's a brilliant picture, but if that is all through the material or just a section of that.
Thank you for your question. In image part E, you can see the agglomeration in that regions of that figure. And some regions of image, you can see the most homogeneous distribution, but some of the regions, you can see the agglomeration part of silver nanoparticles. This part E taken from the homogeneous part of the image. This is the reason of the difference.
What is the magnification of picture A? I don't see that, that's why.
It doesn't record it in that image, I don't remember. I don't know.
This is in white and sense of that's why. Okay, thank you.
Thank you.
Okay, any questions? Thank you. Thanks. Okay. Now, our third presentation will be delivered by Professor Sabit Adanur. Their work is the development, effect of fused deposition modeling or FDM processes parameters on mechanical properties of woven polymeric structures. And the team is Sherry Kaji, Jumeri, Ashok Sapkota, Sabit Adanur, Emel Kurum, and Recep Önder.
Thank you. Good afternoon. Thank you for coming for this presentation. Today I will be talking about effect of fused modeling, fused deposition modeling process parameters on mechanical properties of woven polymer structures. And this work is done by a team. Currently I am at sabbatical at Gebze University. And my graduate students, Shri and Ashok, work in this research at Auburn University in Alabama, in the US. And at Gebze Dr. Emel Kuram and Dr. Recep Önder are cooperating with us. Probably you know additive manufacturing by now. In Turkish, I guess it is called eklemeli imalat. This is making the objects layer by layer, putting on top of each other. This is in opposition to subtractive manufacturing, which has been used for centuries, such as machining, molding, etc. But now, within the last couple of decades or so, 2-3 decades actually, there has been emphasis on additive manufacturing of structures. And we can make very complex shapes with the additive manufacturing. And as you know, textiles are very complex shapes made of fibers and then yarns and then fabrics. So that's what we are trying to do. Again, the textile manufacturing process is very involved, very complicated, starting with the polymer, and then through fiber spinning, we obtain the fiber, and then through yarn spinning, we obtain the yarn. And there are different fiber spinning methods, as you know, as well as different yarn spinning methods. So it's a very complex process. And also we are dealing with the fibers, which are flexible, so short, it is very difficult to control them. And then once we obtain the yarn, then we make fabrics using either weaving, knitting, braiding, or tufting. Or for the non-woven manufacturing, as you know, we go directly from polymer to fabric, bypassing fiber and yarn manufacturing stages. So this is a long process, very expensive, although it is not appreciated that much, but very, very long process, time-consuming, tedious, and expensive too. So what we are trying to do really to eliminate all those middle processes and try to go directly from polymer to fabric, whether it is woven, knitted, braided, or tufted fabric. But we realized that in the process, we should manufacture the filament first. It is not very practical to go directly from polymer to fabric, but we have to make the filament in the middle. These are the additive manufacturing techniques. As again, probably you know, sheet lamination, material extrusion, which is FDM, direct energy deposition, powder bed fusion, material jetting, bed photopolymerization, and binder jetting. So in FDM, fused deposition modeling, this is the schematic of the equipment shown here. And this is the fabric piece that is produced. So as you know, probably we have a nozzle that moves in the XY directions, and then the plate usually moves in the Z direction. Therefore, we have all XYZ movement to place the polymer in the fabric. So the filament is already made somewhere else. Usually it is a composite. In this case, we use PLA filament, and then it is heated and extruded in the nozzle by the nozzle, and then deposited on the fabric here, layer by layer. And again, the plate moves, and then after that, it is the polymer is cooled and solidified, and therefore the fabric is obtained. Well, we have to define the fabric design first, and that's what we did using the SolidWorks. We chose 2-1 twill design, but you can choose any woven fabric or braided fabric design. We did others as well, but in this presentation, I'm going to talk about 2-1 twill. We have to define the fabric structure very well, including the diameter of the yarns, the distance between the yarns in X and Y directions, and then between warp and weft. So every detail of the fabric has to be defined to be fed to the machine, additive manufacturing machine. So that is done first, and then we have to set the printing profile on the machine, such as layer height, print speed, infill speed, wall speed, and travel speed. The layer height is the amount of the thickness of the material that we put on top of each other, layer by layer. print speed is the movement of the nozzle. Infill speed, how fast you fill inside the structure, so you would have dense or less dense structure. And the wall speed also, how fast or slow you make the wall. Again, that affects the height of the surface. So, okay, these are the three printing profile. High detail is very precise, high quality part to produce high quality part. Standard is medium quality, and high speed is less quality but faster production. So those are the machine parameters that we can choose. And then we did the experimental design. We produced 9 samples using the high speed, standard, and high detail printing profile. And we chose 3 different temperatures, 205, 220, and 235 degrees. And these are the default values of the machine for high detail, standard, and high speed. But we ended up using these numbers to be able to produce what we wanted. And some definitions here related to the machine. Retraction distance is how much filament is removed from the hot end during regular retraction moves. And maximum retraction count it limits how many retractions can be performed during the minimum extrusion window. Retraction minimum travel is the minimum length of the travel that the extruder must take before forming a retraction. Minimum extrusion distance window is the length of the filament to which the maximum retraction count is applied. So if you have maximum retraction count 10, and then minimum extrusion distance window 2 millimeter, then the printer will only retract 10 times for every 2 millimeter of the filament. And these are testing conditions. Again, we use PLA as the material. We made fabric samples, 30 yarn each in the warp and weft directions. So this is here is the fabric structure that we made, a square, 30 yarn in warp and weft directions. Again, we have to specify the diameter of the yarn, cross-section area of the yarn, gauge length for tensile test and flex test, strain rate, span length, etc. Loading speed. Those are typical values for testing. Okay, for the results and discussion, this shows the quality of the surface of the printed fabrics. Low temperature here, medium and higher temperature, using the high speed to produce faster, standard speed, and high detail or low speed. These are the results for the yarns. So after we make the fabric, we take the yarns from the fabric, and then we tested them for mechanical strength. Again, at different temperatures, different profiles. We realized that the tensile strength in the warp direction is a lot higher than the weft direction. And that is because the nozzle moves continuously along the warp yarn, but for the weft yarn, it is in the opposite direction. Therefore, it moves very slow to fill the cross-section of the yarn. So we have very short addition of the polymer in the weft direction in the cross-section versus the warp is a long filament or long print. So that's why the warp yarns are a lot stronger than the weft yarns in the structure. So the highest tensile strength we observed was 45 megapascal at 205 degrees Celsius. Also, standard printing profile gave higher tensile strength at every temperature. the average tensile strength was not affected by the temperature much. This is two-dimensional graphs, and we tried to make it in 3 dimensions, but we realized that we need more data points to make it a smoother curve rather than sharp curves like that. And then the modulus from the tensile test again. Modulus actually decrease slightly with increasing temperature, and that's probably due to degradation at higher temperatures. And at 205 degrees Celsius, we obtain around 9 gigapascal modulus. Again, this is the 3-dimensional representation of the same data. Then we tested fabrics in the warp and weft directions. These are individual test results, force versus displacement in the first one. And then for the warp, and the second one is for the weft, again, force versus displacement for individual tests. Again, here the same result. The tensile strength in the weft direction is significantly lower than the warp direction for the same reason, because the way the polymer is laid down in the warp and weft yarns is different. Okay, then the results are shown here. Again, the warp is in blue, and the weft yarn is in, I guess, yellowish color. And you can see the difference in tensile strength for the warp and weft yarns, again, because of the same reason. Because of the way the polymer is deposited in the structure. And this is the modulus. Again, the warp direction modulus is a lot higher than the weft direction modulus. So there's a problem in making these fabrics with the additive manufacturing. Somehow we have to increase the tensile strength and modulus in the weft direction. And those are shown here in 3-dimensional graphs. Again, as I said, we need probably more data points, more than 9 to 12 smoother curves, so that there will be a better representation of the results. And then we did the flexural test, 3-point bending test for the warp yarns and weft yarns, warp on the left, weft on the right. Again, we observed the same thing. The warp direction performed a lot better than the weft direction for the same reason. The maximum force at 5% strain is reported to be 20 Newton in the warp direction and 8 Newton in the weft direction. Again, big difference there. These are the 2-dimensional results of the flexural tests. We observed that temperature really does not have, has different effect in the warp and weft direction, just like tensile strength. The flexural strength in warp direction is a lot higher than the weft direction. This is the modulus, flexural modulus results. Again, same thing. The warp direction is a lot higher than the weft direction modulus. One thing we noticed that in flexural modulus, in the weft direction, increases with increasing extrusion temperatures more than the warp. But printing profile does not have much effect on the flexural modulus properties. These are the results for the same results in 3D. Then overall, the optimum or the best properties, best conditions to obtain the best properties are given here. The first column is the parameter. For example, tensile strength. The highest tensile strength for the yarn was obtained with the standard printing profile at 205 degrees Celsius, and the result was 44 megapascal. Tensile modulus was obtained, the highest or the best tensile modulus was obtained with high speed at the same temperature, and that is the result. And then for the fabric tests, in the warp and weft directions, for the tensile strength and tensile modulus, they are given here. And then for the flexural strength and flexural modulus, they are also given here. So these are the best results of our tests obtained under those conditions. Okay, we are trying to, the purpose here is to reduce the development and then manufacturing time of the fabrics. But there are some challenges. It is not easy to have a flexible structure using extrusion. That's one challenge we have to, especially PLA is not very flexible structure, flexible material. So in other work, we mixed it with TPU to make it softer, but there's a challenge with these manufacturing methods. That's one thing. Also, it is difficult to control the process parameters to make very fine yarns. So far, really, we couldn't go below 1 millimeter diameter, but we are working on that. Also, there is lots of empty space in the fabric structure, so it is difficult to make those or to allow those empty spaces. Because of those empty spaces, it is difficult to control the flow of the polymer. And also, we need to have small areas of support when the yarns are passing over each other without touching each other. So that is also a challenge. So these are the conclusions. Extrusion temperature and printing profile influence the surface and mechanical properties of the printed yarns. Less surface roughness at lower temperatures, as increasing extrusion temperature increases streaming or material flow, as was shown earlier. Best surface profiles obtained using high detail printing profile, which is expected because you are producing it slower at a higher precision. Tensile properties are found to be affected by the process parameters for the individual yarns, and standard printing profile provides the maximum tensile strength. Tensile strength changes a lot for the warp and weft directions, and the modulus is the same. The effect of temperature is not that critical for tensile strength. For the flexural strength, again, it is high in the warp direction. It does not depend on the print profile, though, that much, except lowest temperature. There was a trend, clear trend at the lowest temperature, but in other temperatures, the trend was not there. Flexural modulus is higher for low extrusion temperature in the warp direction, increases with extrusion temperature in the left direction, which is a little bit unexpected or different than the warp direction. But overall, printing profile does not have much effect for the flexural properties. Again, this is a joint project between our university and the Technical University, and we thank those departments for their support.
Okay. Any questions?
Sabit Hocam, thank you very much for coming here and presenting this pioneering work, I believe. In the last ULPAS, we have also listened to this presentation, and there was the question of hairness and the replacement of hairs in this additive manufacturing. In fact, I see, although you are referring it as warp and weft yarns, they are more monofilaments, are they not?
Well, yes and no. If you go back to that. So if you look at here, this is is the west direction, this is the north direction, it's a little bit curved picture. But you can see the individual filaments in the both direction. Although they are kind of together, but you can identify individual filaments in the both direction. So it is multi-filament really. But since they are glued together because of the extrusion, they look like a monofilament and act like a monofilament, but really they are multi-filament structures. In the west direction, it is different. As I said, the polymer is deposited on top of each other here, layer by layer. And so you don't see that filament visibility here much in the left direction because of the nature of the process.
Thank you.
Thank you so much, Prof. It was very nice and interesting presentation. I've got two questions. One is that we have to produce those kind of fabrics vertically, because if we want to produce when they are laid down on the ground, we cannot produce the interchanging movement of the bar and weft under and over each other. And when we go to the finer filaments, it will be much more flexible and we cannot produce them vertically because they cannot stand on their own feet. So what is the solution for that?
Well, the solution is to have a support material that will be included in the structure, but then after the fabric is made, then it will be dissolved and moved away from the structure. That will be the solution.
That's a perfect idea. And my next question is that at the end of the day, whatever we produce with the three-dimensional printing is going to have lots of shrinkage because we are not going to be able to orient the polymers. It is not oriented polymers. And with that problem, is the 3D printing going to be a real answer to fast production from polymer to product? Because it is not oriented.
Okay, if we, for the first part of the question, it is during the solidification, there's some orientation, especially in the board direction more than probably the left direction. So, but the initial application areas of these structures would be monofilament fabrics. For example, for filtration, monofilament fabrics are used, so this structure would be good for filtration, or fabrics that are used in paper making, those are also monofilament fabrics. So these are the starting points for this, but eventually, once all those problems are solved, then we may have finer filaments and more flexible structures. With the inclusion of the thermoplastic urethane, TPU, we mixed it with the PLA, although it was not part of this board. So we have flexibility in the structure. It is not very brittle or stiff. But to have just like a regular fabric at a fine level, I think we still have a long way to go.
Thank you so much. Excellent.
Any questions? I think there is no question. Thank you, Professor Savi.
Thank you. Spor olarak Fenerbahçe'ye götürecek. Onların daha çok ihtiyacı olacak.
Okay. The fourth presentation today belongs to Bedriye Çukunar, and her topic is the preparation and characterization of pH indicative films based on polyethylene succinate anthocyane.
Hello everyone, I'm Bedriye Çınar from Ege University. My topic is preparation and characterization of pH indicative films based on polybutyl and anthocyanin. Thank you for being here. I hope it will be helpful for you. Firstly, I'm going to talk about the topic, the introduction section. We know that the 99% of the annual plastic production of approximately 345 million tons is petroleum-derived polymers. So we have a huge amount of some environmental problems about this. So the petroleum-derived plastic packaging materials are commonly used to preserve some foodstuffs and also some other main foodstuffs. So plastic packaging constitutes some 35% of plastic products produced over 450 million tons annually. So also the 46% of the global plastic waste production of more than 340 million tons annually consists of packaging materials coming from packaging materials. So in here we have to solve these problems by using bio-based and biodegradable polymers, because we know that the petroleum resources are finite and plastics have high environmental damage. So in here we can use biodegradable polymers. They can be derived indirectly or indirectly or directly from renewable sources. And then we know that bio-based polymers indirectly synthesis from renewable resources. So they stand out with good film forming abilities compared to natural counterparts, and also suitability for some industrial processes like extrusion, injection, and blow molding processes. In this study, I used this polybutylene succinate polymer. It's a bio-based and also biodegradable polymer. It's synthesized from bio-based butanediol and also succinic acid. So it's coming from sustainable resources. It's also biocompatible, and also FDA has approved bio-based PBS for food contact. It has some medium-range mechanical properties and good flexibility. It has good oxygen barrier and also low melting point to produce with extrusion. So, but we have to apply new functional properties to use as some food packaging materials. It may be sometimes smart packaging and also sometimes active packaging. And also it has some low water vapor barrier. And of course, it has not any antibacterial efficient activity on. Actually, the food packaging should not only support the transportation and storage, but also prevent food waste and also protect the human health. So we know that 1.3 billion tons of edible food are lost or wasted annually in the supply chain. So the consumers, we often discard these foods based on the expiration date. There are some expiration dates, and we discard these foods based on these dates. These leading to waste of safe and edible products. So the expiration labels actually primarily indicate the quality degradation rather than safety, because we discard these foods, but these are the still safety actually. So these traditional labels don't provide any real-time information about our foodstuffs. So they don't give any information about the freshness and also spoilage of these foodstuffs. So in here we have to use some new innovative solutions for the smart packaging. So we can use some active packaging for the antibacterial efficiency, and also we can use some smart packaging, and also in here especially smart labeling to show the freshness or spoilage of our foodstuffs. So these smart packages or labels communicate with consumers, can provide some information about the quality and also freshness of our foods. In some fresh foods, some gases released by spoiling products. such as some carbon dioxide, ammonia, and also hydrogen sulfide. So in here, these spoiling releasing gases causes some pH changes in the package environment, of course. So if we show these pH changes by using some different color changing packaging or labeling materials, we can detect these pH changes. So these are some pH sensitive indicators. We can use some different indicators detecting the pH changes. So in this case, we can observe some spoilage of our foodstuffs, especially in some meat and also fish products. It's important because these meat and fish where freshness monitoring is critical in here. So we can use some different pH sensitive indicators. There are some traditional indicators, but now some natural colorants can be used for pH indicative materials. So there are some different natural colorants, some like bethanins, curcumins, and also anthocyanins. In here, the anthocyanins is some non-toxic, sustainable, and sustainable natural colorants. It has broad color change. It's extracted from some red cabbage and also eggplant, black palm, blueberry, blackcurrant, and etc. There are many resources for anthocyanin, and it has broad color change. Its color is red at pH 2, and it goes pink to purple blue at pH 6, and also it goes to yellow or green at pH 10. So in this case, we can use this anthocyanin by indicating some different changes of pH. So in this study, the aim is the extraction of anthocyanin from red cabbage. We used red cabbage to extract the anthocyanin, and also producing these anthocyanin-loaded polybutylene succinate films. So the films including different weight ratios of anthocyanin. There were 1, 2, 5, and 10 weight percent. We used some melt compounding technique to produce these packaging films, and some physical and chemical properties of the films were determined, and also applied some different packaging application to see some indicative properties. So now I want to continue with experimental part. The experimental part of the study includes two stages. The first one is the extraction of anthocyanin, and second one is film preparation. The anthocyanin extracted from red cabbage leaves by using some acidification techniques. We obtained anthocyanin powder by extracting methods, and we mix this powder with polybutylene succinate. And then these materials fed to some twin screw extruder. The compounding parameters are 135 degrees Celsius, 100 RPM, and 3 minutes. This is total time for the mixing process. We add the anthocyanin at the end of only 45 seconds. Okay, so because it has some different thermal sensitivity, so we add this anthocyanin only 45 seconds, and then we obtain some PBS anthocyanin blend granules, and finally the compression molding is used to obtain the films. So we characterize our films by using some different techniques, FTIR, TGA, some morphological imaging conducted by using scanning electron microscope, and also antibacterial activity, pH response by using different buffer solutions, and also some packaging studies on the meat, chicken. So firstly, I will start with chemical properties for your transform infrared spectroscopy. As you've seen here in figure 1, you can see the first spectrum of anthocyanin, it has some broadband at hydroxyl stretching vibration, 3,200 around wave number. It has broadband hydroxyl stretching, and also there are some different characteristics of some different flavonoids in the structure of anthocyanin. It also has some angular deformation of the phenols. There are some different phenols in the structure, and then different characteristics of flavonoids of anthocyanin. So these spectrum show that we extract the anthocyanin from red cabbage. And the second graph, figure 2, shows the filter spectra of the films, pure PBS film and also anthocyanin including films. So actually there are no any peak sheets and also new peaks in the structure. We can say that the composite films has same filter spectrum with pure PBS. So in here we can say that there are some physical components. So the other characterization is morphological properties. In figure 3, there is some micrograph of the R films from the cross-sectional area, fracture surfaces area. So the first image shows the pure PBS film. There are some rough and brittle structure of the PBS, and if we add the 1% of anthocyanin, there were some false separation of the structure, and also we showed that some ductile fracture surfaces according to pure PBS film. So, and also we observed some higher elevation compared to pure film. But on the other hand, there are some distinct agglomerations on the structure, especially in false separation region. If we increase the anthocyanin amount to 5 and 10%, so the quantity and size of agglomerates increased. So in here, especially in 5 anthocyanin film, some green arrows shows the voids between the pulling of some agglomerates from the structure. So actually, I can say that there was some heterogeneous distribution of our anthocyanin in the structure. This may be due to some low mixing time in the extrusion process. So the other test is thermogrametrical analysis. Actually, we want to see here the thermal stability of our anthocyanin. So in the table, you can see some degradation temperature of anthocyanin and our films. So anthocyanin has thermal degradation, T onset value is 192 degrees Celsius. We process this anthocyanin in extrusion at 135 degrees Celsius. So in this case, we can say that we have some thermal stability during the extrusion process. And then if you look at the PBS and the PBS films, PBS, of course, exhibited a single-step degradation curves, indicating the decomposition of main chain of PBS. If we add some anthocyanin in the structure, the degradation temperatures actually show the progressive decrease, which is due to the low thermal stability of anthocyanin, and also anthocyanin contributes to earlier degradation of these films, and also facilitate the separation of some volatile components in the structure. Which compromises some integrity of the films because there were some false separation in the structure. Another test is the antibacterial activity. The antibacterial activity of the films against some foodborne pathogens, Escherichia coli and also C. aureus pathogens was determined by observing some inhibition zones after 18 and 24 hours incubation. As you see in the image, there are some 18 and 40. 24-hour incubation times. So there's yellow points shows the R films. We know that PBS has no any inhibition zone, so it has not any antibacterial efficiency. So if you look at the anthocyanin including films, there are no any colonies on the surfaces of any films. So for either E. coli or iris. So if you look at the 1% anthocyanin and 3% films, they did not show any distinct inhibition zone in the structure in the crest. But if we increase these anthocyanin amounts to the 5 and 10%, there were some clear inhibition zones were observed for both bacterial species. So especially in 10%, displayed strong antibacterial efficiency activity due to the, especially in the migration of this anthocyanin to the agar medium. There are some releasing migration of this anthocyanin. And then we look at some pH response of our films. We know that as pH increases, the anthocyanin colors change, red to pink, and then purple, and finally yellow-green tones. So if you look at the 1 and 2% anthocyanin films, there were no change, our films colors. So there is no any pH indicated behavior in these films. But if we increase the percentage of anthocyanin to 5, there were some different color shifts in here. So at pH 2, the film is actually dark red. So, and then it's starting at pH 8, color shifts to blue and purple color. So, and then if we increase the pH 12, the color further changes to green. So, if we increase the anthocyanin amount to 10%, similar color transition as in 5, with red shifting to the blue, purple, and eventually to green at high pH levels, 12 levels. There are some shifting of the colors. But in here, high anthocyanin amounts lead to some migration from the film to the buffer solution. So this reducing the stability of our films. So the anthocyanin goes to solution in the buffer solution in here. So we can say that 5% of anthocyanin provides some most reliable pH response, color change without significant migration. So, and finally, we applied some packaging application in some chicken. So PBS anthocyanin initially exhibited color from light pink to the dark red, depending on the amount of anthocyanin. So some fresh chicken actually has pH around 5.5. Actually, if we spoil these meat, a pH above 6 is generally considered an indicator of spoilage of this meat. So the pH increases as the storage time extends, of course, and then the meat spoils. In here, we applied some 4-day chicken storage of our films. The first image shows the pure PBS films. Of course, there were no any color change in here. And then if you look at the 1% anthocyanin, also there were no any color change. It's not any pH responsive behavior. So if we increase the anthocyanin amount, we saw that some transition, some shifts of the colors of these labels. So 2 anthocyanin shows slight transition from light pink to the dark pink. And then the 5 anthocyanin shifts to red to purple, and the 10 is changed from red to dark blue. So in this case, in here in the meat spoilage, 5% and 10% of anthocyanin provides some noticeable color shift in the meat spoilage. It's suitable for this, some use as pH indicators for the meat. It can be also used in fish products. In conclusion, we anthocyanin extracted from red cabbage, and the films were produced via melt compounding and compression molding technique. And we obtained some physical blending between the components, and in the extrusion process is suitable for the anthocyanin because there were no internal weight loss in this extrusion temperature. And finally, some 5% and 10% of anthocyanin exhibited strong antibacterial activity against some foodborne pathogens. And finally, I can say that these 5 anthocyanin and 10% anthocyanin films can be used as pH indicators for some meat products, for some chicken spoilage. Okay, thank you for listening.
Thank you, Betriye. Any questions from the audience? Okay.
Thank you very much for this presentation. Interesting. Is there any relays from your films? Do you carry out the relays test?
No, we don't perform yet release test, but we saw that in here in the buffer solution, especially in 10%, there were many large amount of migration from the films, and also, of course, there were I think there were some releasing from the structure, but still we don't apply any releasing test yet.
Okay, thank you very much.
Thank you.
Thank you very much. This nice presentation. It's interesting results. There are commercially exploited food colorants.
Yeah.
Much more effective than these you used, including red cabbage. One of them is, beetroot. It's commercially exploited and used as a food colorant. Saffron is a very strong. It's used. And mites, they are sold in the market and more producing more colors than these. So next time, possibly it may be a good idea to use more effective and commercially available products.
Yes, yes.
So that you can quickly commercialize your idea.
Yes, in here actually there are some commercial anthocyanin, but all of them don't exhibit pH responsive behavior.
Have you tried this?
Actually, we take some commercial anthocyanin and we can't not see any these pH changes. Maybe it's some different resources, maybe some blueberry and etc. The resources of this anthocyanin changes the pH responsive behavior, of course. So in here we used red cabbage, especially in black carrot is more effective than red cabbage. And then, as you say, we can use some saffron and also some curcumin and also some betanin is many have some pH responsive behavior. So we are trying different natural colorants.
Mite also, the mites used as a, it is already, available in the market in this country also. Used as a food color by pastries or, pastas or something like that.
Yes,
it's used.
Okay, you can try, thank you.
Betria, thank you very much for this interesting work and interesting results. You are using PBS and you are making film packaging for food packaging. This is very interesting. And you are also trying to make an active film for the spoilage of the food. I wonder if the PBS will work in fiber form in the same direction. Have you tried or do you plan to try in nanofiber or non-fiber form?
Yes, our research group in Kocaeli University, Ayşe is working about the electrospinning of these polyethylene succinate. And we don't try some fiber spinning techniques instead after some electrospinning techniques, but we have some dry spinning machine in our lab. We can use this. We thinking about this because polybutyl 6-8 has some behavior about fiber forming, because we use some injection molding methods, different parts, and it's during some tensile testing, it's elongating as fiber form. So it's actually good for fiber forming.
That will be interesting.
Yeah.
Thank you.
Any questions? Okay. Thank you. Thank you very much. This session's last final presentations, I think, is the polyhydroxyethyl methacrylate modified cellulose nanocrystals and their PBAT-based nanocomposites, and will be presented by Deryan Yılmaz Arı. Yes.
Good afternoon. I will present our study today from sustainability and ULPAS geometry. As it is mentioned that most of the plastics are obtained from petroleum-based raw materials. However, we need to reduce their usage for the environmental concerns. So, in the recent years, the biopolymers and their composites have gained attention for that reason. Also, our study is a bio-nanocomposite. Firstly, I will mention our material and then our nanoparticle, and also I will mention that what is our challenge and the solution. Also, I will talk about our study's aim, and I will show some results of that. We chose PIVAT. What's that? Polybutyl adiphate coterephthalate. This is the PIVAT structure. It's an aliphatic aromatic copolyester. Why we chose this? Because it is biodegradable, it has high flexibility, toughness, ductility, and good pressability. But we can improve its strength and stiffness by making a nanocomposite. And we use for that cellulose nanocrystals as nanoparticles, because it's called CNCs shortly, because CNCs have stereomechanical and physical behaviors, and it has low density, high surface area, and it has diversible chemical reactivity. Also, it's biocompatible, and there are abundant resources to obtain to CNCs, because it's coming from cellulose, also it's coming from the plants, and it is the lignocellulose, and it includes the hemicellulose, lignin, and cellulose here. How the CNCs are obtained from the cellulose? This is cellulose fiber, and it includes the crystalline regions and the amorphous regions. By the strong acid hydrolysis, mostly the sulfuric acid hydrolysis method, the amorphous regions are hydrolyzed in the acidic medium, but the crystalline regions remains, and after the centrifugation, dialysis, and ultrasonication, the highly crystalline, rod-like CNC structures are obtained. However, there is a challenge to be used the CNCs. This is the structure of the CNC, and it has stroke hydrogen bonds. You can see that here, and also it is highly hydrophilic structures. But we want to make a composite with PIVAT, and most of the polymers we all know that they are hydrophobic. So we want to make CNCs to be hydrophobic, to make a composite with PIVAT. So how we can overcome with this challenge? We need to make surface modification of the CNCs. For example, you can see that in the polar media, the CNCs like the polar media because they are hydrophilic. But after the surface modification, they are not like anymore here. There are different methods of the CNC's surface modification. I didn't mention by one, but I can give some examples of that. For example, at esterification, the hydroxyl group is replaced by the ester groups. For example, at silylation, the silane molecules binding onto the CNC surface. I want to mention especially for the grafting onto and grafting from methods, because we use the grafting from method on our study. What are they? At the grafting onto method, this is our CNC surface. The polymers are directly attached on the CNC surface with their terminal end groups. On the other hand, at the grafting from method, this is the CNC surface also. The monomers are attached with the initiator and polymerization occurs on the CNC surface. For example, it can be the ring opening polymerization or free radical polymerization. And what did we do on our study? As I said, we use grafting from method. We used HEMA, what is that, 2-hydroxyethyl methacrylate as our monomer. And we use TPS as potassium persulfate, it's an initiator. And we use water, which is environmentally friendly for our solvent. And we grafted from HEMA to CNC surfaces here. And we called like that, CNC grafted polyHEMA. And what are aims of the study? As I said, we want to synthesis of modified CNCs. And we want to make different chain lengths on the CNC surfaces. I mean that we will make we used different amount of HEMAs to obtain a different length of the P-HEMA chains on the CNC surface. After that, we make our nanocomposite with pipette at MAP mixer, and we look at their rheological and thermal properties. It's our material, as I said. I didn't mention only the letter. We used it for the precipitation. I explained, but here, like that, when we used 1 ml of HEMA, we used like the CNC GP HEMA 1. It is the shortest chains of P-HEMA CNC have on the surfaces. And at this one, we added 5 ml of HEMA, and it is CNC GP HEMA 5, which has the longest chains on the CNC surface. And our reaction conditions was 3 hours at 70 degrees in an oil bed. After that, as I said, we make our nanocomposites with pipettes. Let's look at some of our results here. This is an FTR analysis of neat CNC and modified CNCs. You can see here, this is a neat CNC, and you can see sharp peaks here. This corresponds to the carbon-oxygen double bond, which HEMA has these bonds. So we can say that this is all the modified CNCs. We can say that we can successfully make modified CNCs here, because we see that the carbon-oxygen double bonds. And this is some of our rheological results. You can see that the complex viscosity, also the storage modules, is increased when we use the CNC GP HEMA 5, which has the longest chain on the CNC surfaces. When we make our nanocomposite with this one, the complex viscosity and also the storage modulus are increased. This is a TGA curves of the neat CNC and the modified CNCs. This is the black one is the neat CNC, and as you can see that its thermal stability is about 30 degrees here. But when we make our surface modification, when we grafted the HEMA on the CNC, their decomposition temperature is getting lower here. Also, this is the DSC analysis of the cooling curves of our nanocomposites. This is the PBAT with CNC-GP HEMA 5. As I said, this one has the longest chains, longest HEMA chains on the CNC surfaces. The crystalline temperature, when we compare the other ones, the crystallization temperature is getting higher. You can see that, but for the degree of crystallinity, we didn't see any dramatical change here. So as a conclusion, we mentioned that the CNC dispersion is better when we used the modified CNC, which has the longest HEMA chains on the CNC surfaces. And with these improved dispersion and the increased interfacial interaction between the P-HEMA and PBAT, the complex viscosity, also the storage modulus increases. Also, when we look at the thermal ones, at the TGA graph, we see that the modified CNC starts to decompose at lower temperatures than the mid CNC. Also, from the DSC analysis, the crystallization temperature getting higher when we grafted longer chains to the CNC surface. But as I said, we didn't see any dramatical change for the degree of crystallinity. This study is supported by İTÜ, Science Academy, and Turkish Academy of Sciences. And our research group is SGPL group. Thank you for your attention.
Thank you, Eda. Any questions from audience? I think there is no questions. Okay. So, this is the end of our session today. I think the coffee break time now it starts. So you can go and drink your coffees while visiting the poster session.
Good afternoon. Thank you for coming to this session. In this session, we have 4 presentations. The first presentation will be made by Meryem Sabzi Mubareke. A little bit background about her. She had Bachelor of Textile Engineering degree in Fiber Science from Amitabha University of Technology in Tehran, Iran. A Master of Textile Engineering in Fiber Science, again from the same university. And then she has work experience as intern in NAH company and Lyco group, both in Iran. The title of her presentation is Synthesis and Melt Spinning of Thermoplastic Cellulose, a short review. Thank you.
Good afternoon. In this review, we're going to talk about synthesis and melt spinning of thermoplastic cellulose. I'm going to explain the cellulose extraction, esterification, and thermoplastic cellulose melt spinning. Introduction. New generation of textile fibers, such as recycled and bio-based fibers, are produced with a focus on environmental sustainability issues. These fibers are being developed in many countries. Cellulose makes up a significant amount of fibers used in textile industries. This fiber is the most abundant polysaccharide in nature. It's biodegradable and linear. It's made up of glucose units linked by 1 to 4 glucosidic units, linkages, and it has 3 hydroxyl groups, which makes it insoluble in water and common solvents, and lack of thermoplasticity. Some cellulose sources are cotton, wood, agricultural waste, algae, and bacteria. Lignocellulosic biomass consists of 3 main components: cellulose, hemicellulose, lignin, and a small amount of other components such as pectin, waxes, proteins, etc. Cellulose extraction include pre-hydrolysis in order to open the biomass matrix, alkali-assisted pulping, and bleaching in order to improve the cellulose content and whiten the final product's color. Cellulose derivative synthesizing can occur under homogeneous or heterogeneous conditions. The advantages of homogeneous systems compared to heterogeneous ones are reproducibility, lower temperatures, and the ability to control the degree of substitution. And here are some cellulose esters and ethers. Three kinds of thermoplastic cellulose derivatives are reviewed in this slide. Cellulose monoesters such as cellulose acetate and cellulose butyrate are produced with single acylation reaction. Cellulose mixed esters such as cellulose acetate propionate and cellulose acetate butyrate, or CAB, are produced by dual acylation reaction. And another thermoplastic cellulose is long-chain cellulose esters such as cellulose octanoate. Literature review. 2 ways of cellulose extraction from cotton linter are reviewed in this slide. 1-stage extraction and 2-stage extraction. In 1-stage extraction, Hibachi and co-workers used 3 methods is using sodium hydroxide, and sodium sulfide, sodium hydroxide and sodium hydrosulfide with different concentrations and temperatures in order to extract the cellulose. The results showed that cellulose content for all the samples was over 97%. And by increasing the temperature, the degree of polymerization decreases. In two-stage extraction of cellulose using different temperatures and sodium hydroxide concentrations in stage 1 and stage 2, the results showed that the cellulose content for all samples was over 95%, and the best result was for high sodium hydroxide concentration in the first stage and low concentration in the second stage. And this is because the high OH ion in the first stage can improve the lignin removal. Cellulose can also be extracted from other sources such as sugarcane bagasse, wheat straw, ears of corn, short flax fibers, wood, and waste cellulosic fibers. But the problem of these resources are some of them have low cellulose content, and so that we need multi-stage process, and it makes it hard. Cellulose would be synthesizing under heterogeneous condition by using pyridine and iodine as the catalyst was done, and the results showed that the iodine catalyst caused lower degrees of substitution, and the degree of substitution is dependent on the time of the reaction time actually. But the problem of this method is lack of thermoplasticity. Lack of reproducibility. In lithium chloride and dimethylacetamide homogeneous system, we are able to control the degrees of substitution and reach high degrees of substitution. But the difficulty of recovering the lithium salt is the reason that this method didn't become commercial. But the good properties of the final products and the uniform properties makes it used now. Ionic liquids are other cellulose solvents that can dissolve cellulose in a very short time. Ionic liquids have good chemical and thermal stability and low reaction temperatures, but because of their very high price of them, the usage of them is limited. In CO2, the DBU and DMSO homogeneous system, we can reach wide ranges of degree of substitution, but the low reaction of the low temperature of the reaction is the advantage of this method, but the reaction must occur under high pressure condition, and that's the problem of this method. For fiber melt spinning from cellulose derivatives, viscosity controlling can occur by using an appropriate plasticizer or using a cellulose mixed esters. Toray Industries successfully produced man-made cellulosic fibers called Flores by using cellulose acetate propionate and polyethylene glycol. These fibers had a good moisture absorption compared to PET and better mechanical properties compared to cellulose triacetate. The results showed that the elongation viscosity increases with the reduction of the temperature, and this increasing happens with a sharper slope for cellulose acetate propionate compared to PET, and this is because of the stiffer cellulosic backbone of cellulose acetate propionate. The solidification occurs at 100 centimeters below the spinneret for PET and 20 centimeters below the spinneret for cellulose acetate propionate. And this shows the necessity of applying changes in spin line for metal spinning of cellulose acetate propionate. Cellulose, in research, cellulose acetate butyrate using a plasticizer and cellulose nanocrystals as the reinforcement were melted spun at 160 degrees of Celsius. But the fibers had low strength because of the using the plasticizer and the low molecular weight of the raw materials. In other research, cellulose acetate butyrate was melted spun without using a plasticizer at 230 degrees of Celsius. The point is that the degradation temperature was 275 degrees of Celsius for cellulose acetate butyrate, but because of the shear stress applied in the extruder, we cannot reach higher temperatures than 230 or 40 degrees of Celsius. Large-scale melt spinning of cellulose octanoate melt spinning occurred with a speed of 200 meters per minute. But these fibers had lower strength than the cellulose acetate butyrate fibers melted spun in the previous researches. But the advantage of this method was no need for a plasticizer and melt spinning in 130 degrees of Celsius. And the conclusions. Cellulose acetate butyrate seems to be the most suitable cellulose ester for fiber melt spinning without using a plasticizer, and the rheological condition must be controlled while spinning. Lithium chloride and dimethyl acetamide homogeneous system seems to be the best synthesizing method for cellulose esterification, and it is important to select the appropriate cellulose extraction method in order to reach the appropriate degree of polymerization and cellulose content, and it is essential to control the extraction condition due to the cellulose source. On future prospects, cellulose can be extracted from waste sources, especially sources with high cellulose content, such as paper tissue. Ionic liquids are green solvents that can dissolve cellulose and are appropriate for cellulose esterification. And the most suitable cellulose ester is identified by measuring the rheological properties of the cellulose esters. Thanks.
Thank you, Mariam. We have time for questions.
Thanks, Mariam. My question is that we already have this cellulose acetate, cellulose triacetate, and we can melt spin it. What is the reason behind going to this cellulose acetate butyrate and to go for the mixtures with PEG? What would be the advantage?
Because of the high viscosity of cellulose acetate, we cannot melt spin it with the high high speeds actually. But by controlling the viscosity, as I said, we can control the viscosity by using a mixed cellulose ester, so that we can reach higher speeds for melt spinning.
Thank you. Any other question? I have one. What synthetic fiber was developed to replace or imitate cellulosic fibers, you know? What synthetic fiber, man-made fiber, was made to replace or to imitate cellulosic fibers such as cotton?
Viscose?
Well, it is derived from cellulose, so don't count that synthetic or man-made fiber. Okay, I think polyester meant to imitate cotton fibers. Okay, thank you.
Thank you.
Any other question? Okay, thank you very much. Our next presenter is Hürrem Canıtes. She received her undergrad degree from Bursa Technical University in Polymer Materials Engineering Department in 2021 and master's degree at the same university in 2024. Since 2021, she has been working as a materials research and validation engineer in R&D department of the Salçılar company. Go ahead, please.
Hello, everyone. This presentation and next presentation belong to me. First presentation, I'm going to talk about examining the mechanical properties of basalt, glass fiber, and their hybrid composites. Before starting my presentation, I want to introduce my company which I worked, Material Research and Validation Engineer. Salçılar was established in 1987 and we are a part producer of composites, glass fiber reinforced composite mostly, and we worked for automotive, railway industry, farm equipment, construction area. These are my outlines. Firstly, I will start the introduction. I will give information about the fibers, glass and basalt. After that, I will mention material and method, then test results and conclusion. Basalt fiber is mineral-based fiber and eco-friendly. Glass fiber is, everybody knows, traditional and economic compared to other fibers such as carbon or aramid fiber. And polyester is commonly used resin matrix in composite industry because it is easy to find and cheap matrix. If we compare the fiber properties of glass and basalt, basalt fiber, as I mentioned in my previous slide, obtained from rock. And the mechanical properties is similar to glass fiber, actually higher than glass fiber and cheaper than carbon fiber because, as we know, carbon fiber is expensive fiber and it is not biodegradable, but one of the advantages is a natural source. If we talk about glass fiber made by melting silica, and the glass fiber has wide usage area and cost-sensitive material, and it is also not biodegradable material. In this study, we produced 3 types of composite sample. What are they? One of them is glass fiber reinforced composite, other is basalt fiber reinforced composite, and the last one is glass and basalt fiber hybrid reinforced composite. And we performed some mechanical tests for these materials, tensile test, 3-point bending test, and sharpie impact test. Also, we realized one more test, which is Fiber content ratio. This morning I learned the fiber test content results from my colleague. That's why I couldn't add these results in my presentation, but I will explain the results at the end of the presentation. Material and methods. We used Wolverine and Wolverine glass and basalt fiber in here. Their weight of area is different to each other. That's why the lamination plans changed according to weight area. We used unsaturated polyester, and the production method is vacuum infusion method. That's why we used vacuum infusion method equipments. If we mention production, glass fiber reinforced plastic includes 13 layers. Basalt includes 18 layers because, as I mentioned in my previous slide, the weight of area are different, and the hybrid composite includes 8 layers glass fibers, 7 layers basalt fibers. We use vacuum infusion method, and if we talk about the vacuum infusion method, we put the fibers in the mold, and we applied vacuum bag, and under vacuum pressure, the resin inject the tubes, and we apply this process under 400 millibar vacuum pressure, and we obtain 3 mm thickness composite. Which test we realized? Tensile test, bending test, HY Charpy test, and fiber content test. If we see the results in this table, basalt fiber reinforced plastic has the highest result, highest tensile test result, and the glass fiber result is lowest. But the hybrid composite, we expect these values because literature mentions the hybrid composites is between the glass and carbon, and as we see in this results, hybrid composites higher than neat glass fiber reinforced. Yes, just a little bit higher, but why the result is close to glass fiber ratio, glass fiber test results, because the glass fiber ratio is higher than basalt fiber ratio in this composites. That's why the result is more close. For 3-point bending test, we observed same test results. Basalt fiber has highest value, glass fiber has lowest value, the hybrid composites between them. HY Charpy test is similar to tensile test and flexural test. And before end of my presentation, I want to say fiber ratio contents. All composites fiber ratio is approximately 65%. If we conclude the presentation, we obtain 3 mm thickness composites. We produce 3 different composites: glass, basalt, and hybrid composite. And as we observe in the test results, basalt fiber has superior mechanical properties, and hybridization improves the mechanical properties. We can say that basalt fiber is alternative to obtain higher mechanical properties and natural sources materials. Thanks for listening to me. If you have any questions, I can answer.
Thank you, Hira. Are there any questions? I'll ask one. What was the percentages of those fibers in the composite?
65%.
65% what? Basalt?
Approximately 63% basalt fiber, 65% glass fiber, and hybrid composites also similar. These results.
I'm sorry? Okay.
All results are similar.
All right. Any other questions? Okay, thank you.
I can.
You have one more presentation. I guess we are going to wait to give the certificate for the presentation. Okay, the next presentation again is by Hürrem Canıtez, and the title of the presentation is Mechanical and Chemical Properties of Calcium Carbonate Added Glass Fiber Reinforced Composites.
Thanks. I will skip this slide because I mentioned. For this topic, the outline is same: introduction, method, test, and results. If we mentioned calcium carbonate, we use in the industry, composite industry mostly because its cost effectiveness additives and it can be improve the density and surface hardness of composite, and also it can change the processing and rheology of the composite material, matrix material. With this topic, we used hand layup method. That's why we use unsaturated polyester, hand layup polyester resin, calcium carbonate, which is 32.5 micrometer, and we use chop strand matte glass fiber and rolling glass fiber, and the weight ratio is similar in this presentation. We use homogenizer for adding the additives and also hand layup equipment. This method, we apply the resin on the mold surface and put the fibers. After that, we apply roller and brush step because we want to remove air bubbles in the composite structure. Production step, we have 6 different groups. First, second, third, and fourth group doesn't include any reinforcement material, but the last groups includes glass fiber reinforced material. We use 2 methods for hand layup for reinforced groups and the silicone molds to obtain test materials. This test we realized, lots of tests, as you can see in this slide, mostly 2 main groups, chemical test and mechanical test. In here, viscosity, gel time, peak exotherm, and liquid density for just unreinforced materials, solid tensile test, bending, and barcode test for all group materials we realized. If we compare the viscosity, when we add the calcium carbonate, the viscosity increased. Just 10% added calcium carbonate viscosity similar to neat resin one, but the 15 and 20% added calcium carbonate increased the resin viscosity. It affect the material thickness. Also, it can be affect the resin usage in the composite. These are gel time and peak exotherm test results. When we add the calcium carbonate or any additives, we observed gel time gets lower because the additive makes more reactive the resin compared to neat one. And peak exotherm test values also increased according to addition of calcium carbonate. As I mentioned previous graph, the additives increase the reactivity of the resin. As we see in the second graph, the peak exotherm also increased with related to reactivity. And time to peak exotherm also shorter compared to neat one. These are liquid density results for resin. As we mentioned in the previous slide, I said that the calcium carbonate addition increased the composite density, and as we see in this test results, the addition of the calcium carbonate increased the liquid resin density. Solid resin density also same. We use Archimedes principle in this test method, and as we
see in the blues one belongs to neat unreinforced group, and the greens one belongs to reinforced group. All the samples increase the addition of increased density with addition of calcium carbonate. If we see the Barkol hardness test results, the Barkol hardness also shows the curing degree of composite, because if the value is high, composite has a good polymerization degree. As we see in this result, 10% added calcium carbonate is show higher Barkol value. Maybe it can be caused for normally it should be increased with the addition of calcium carbonate, but composite is not homogeneous material. That's why the results can be changed. And also we observed similar test results in reinforced one, but compared to neat unreinforced group, the 10% calcium carbonate added groups show lower value, but similar to literature, normally if the calcium carbonate value increase, the surface hardness should be increased. In this test result, we can observe this issue, especially 15 and 20% added calcium carbonate shows higher Barkol hardness. The thickness also increased because the resin viscosity was increased. Firstly, the neat group 2.4 mm, but the last group, the highest ratio includes highest calcium carbonate ratio include group has 3 mm thickness. These are the tensile tests. Again, blues one belongs to unreinforced group, and the green one belongs to reinforced groups. We observed calcium carbonate addition is not good for tensile test and also flexural test. Modulus increased because the rigidity increased with addition of calcium carbonate, but the strength is decreased as you see in these graphs. For bending test, we observed same situation like previous slide, but in this section we observe bending modulus also decreased with the addition of calcium carbonate. It can be caused for agglomeration in the composite. We apply homogenizer to mix the material, but as I said in the previous slides, the composite is not homogeneous material. That's why it can be changed in like that. If we conclude this presentation, viscosity, peak exotherm, liquid density, solid density, thickness increase with the addition of additive, but gel time times peak exotherm and some tensile and bending test results get decreased, and Barkol hardness also increased, but we observed some differences in the slides. Thanks for your listening to me. Any questions? I didn't understand.
How many times you repeat the test?
Approximately 10 times, but I will add test results just 5 samples. I select the most similar one. No good one. Similar one because the variation should not be high. That's why I select most common one, close one. Any other questions?
Go ahead, please.
Fiber volume ratio, is it same with the other presentation?
We didn't measure the fiber contact in this study.
What was the purpose of adding calcium carbonate?
Calcium carbonate mostly, let me show, mostly preferred for cheaper additive, and sometimes the composite density wants to increase, and calcium carbonate is cheapest one in the sector, and also some materials has hardness, more hardness according to heat resin one. That's why the calcium carbonate can be preferred. But maybe lower values affect the tensile and flexural strength good side. But in this study, 5 and 10 and 10, 15 and 20% is not good for mechanical testing.
So is it good or bad to add calcium carbonate?
It can be changed because if you obtain high density, yes, it can be good, or high hardness, it can be good, but if you need more mechanical resistance, maybe you can add any different additives.
Any other question? All right, thank you. There are two certificates here of the presentation. Okay, our last presentation is by Professor Dr. Mohammed Ali Tavaniye, and his presentation is, the title of his presentation is Melt Spinning of Polyactic Acid Thermoplastic Starch Blend Fibers, a brief review. Unfortunately, we couldn't print your CV, so you need to talk about yourself when you come to the podium.
Hello everybody, ladies and gentlemen. My name is Mohammed Ali Tabanai. I'm from Iran, American University of Technology, Textile Engineering Department, and I'm honored to present our review paper with the title of Melt Spinning of Polylactic Acid Thermoplastic Starch Blend Fibers. This work is started from 1 year ago, study about a collaboration with Professor Erdoğan, Professor Ümit Halis Erdoğan from Dokuz Eylül University in Izmir. And I must send my thanks to him because this idea is from the Professor Erdoğan about study and starting this project. Initially, I need to say this is a first stage of collaboration. And we had only reviewed many papers, and I want to give my thanks to Dr. Naimi Rad because give me some valuable references to preparing this paper. Let me start with some importance of this study. As you know, bioplastic are already part of our everyday life in many different parts of our life. For example, about the bedding, coffee, cosmetic products, clothes, and fashion, that is very important for us because of our branch and our study, compounding, and etc. Global production capacity of bioplastic, as you can see in this part, is totally 2.18 million tons in 2023. With a human plastic source. So the fibers, as you see here, 21% at its second place about the bioplastic application. As you see here, totally 2.18, as I said previously, in 2023, but you see 31% PLA. It shows us that the PLA is very, very important among the bioplastics. For example, bio-based, non-biodegradable, and biodegradable polymers. 52.1% biodegradable, 47.9% bio-based, non-biodegradable. In 2023, 1 year ago, the difference between non-biodegradable bio-based and biodegradable is small, but estimation to 2028, the global market grow to 7.43 million tons, and the share of the biodegradable fibers grow to 62%, versus the 38% of bio-based non-biodegradable fibers. And this is show you the textile fiber is the second place, the most consumer segment of bioplastics. As you see here, the PLA fibers have a huge share of bioplastic fibers. And finally, melt spinning of PLA fibers has been employed for a long time. We take up speed reaching up to 5,000 net meter per minute. But industrially, it's lower than 5,000. This is only a record. So it's considered the most promising, sustainable, and biodegradable fiber to replace PET in textile products. What are the PLA fibers' advantages and disadvantages? Industrially, biodegradability, reduced carbon footprint, versatility, thermoplastic and melt spinability, non-toxic biodegradation products, acceptable mechanical properties is all the advantages of PLA fibers. So, disadvantages: slow biodegradability, recycling challenges, and hard spinability. PLA is melt-spun, but hard spinning. This is a big issue, but amongst all biodegradable polymers, PLA fibers have the best spinability, and due to this reason, the PLA fibers grows more and more today. Why biodegradability of PLA fibers is slow? Under industrial composting condition, PLA fibers can be composted at temperature greater than glass transition temperature, a minimum of 6 months, usually in 58 degrees Celsius. And biodegrades fully several years. This is so bad for PLA fibers as a biodegradable fiber. Reason of the slow biodegradation is high crystallinity of PLA, hard and impact structure of crystalline region act like a protective walls against biological agents. So, what is the best possible way to modify and improve biodegradability of PLA fibers? After our study about many papers in this area, we found that blending with other bio-based biodegradable polymers or the use of nucleation agents are often necessary. For polymer blending in melt spinning, we can prepare polyvalent fibers with the internal mixing the polymers. For example, PLA with other biodegradable polymers internally mixing with extruders, or in a bicomponent fiber So the bicomponent fiber is a fast way and is more easier than another conventional melt spinning methods. Starch, the most important renewable resources and the second largest source of biomass on Earth after cellulose. But as you can see in the graph, the highest share of this bucket belongs to corn in the first place, and after this cassava, potato, wheat, and others. So the corn is the highest share in the market of the starch. But the starch comprises mainly two types of glucose polymers, amylose and amylopectin. So native starch has amylose exists in an amorphous state throughout starch kernels with a 20 to 25% share, and amylopectin exists only in the crystalline layers, which are subdivided into semi-crystalline and semi-amorphous lamina, with 75 to 80%. But structure, what's the difference in their structure, amylose and amylopectin? Amylose have a linear structure. All of the chains is linear, versus amylopectin that it is branched structure. Molecular weight of the amylose is lower than 0.5 million, but the amylopectin between 50 to 500 million. This is a big difference between amylose and amylopectin. A starch has a more advantage, renewable and eco-friendly, non-toxic, good degradability and availability. But disadvantages: low mechanical strength, hydrophilicity, brittleness, low heat resistance, and poor miscibility with hydrophobic polymers. Low heat resistance and poor miscibility with hydrophobic polymers is our challenges with starch in thermal processing. While starch offers many advantages due to its limitation, researchers continue to explore ways to enhance starch-based plastic for broader applications. What is the major terms in high-speed spinning of polymer melts throughout the spinner hole? As you can see, when the polymer exits from the spinner hole, at first we needed drawability and aligning the polymer chains in line with elongational stress. And after that, we need suitable flow viscosity, melt flow viscosity. Both of them are in contrary of themselves. Drawability, melt flow viscosity. So, as I said, the amylose share in the starch has a linear structure. So, orientation and parallel alignment of amylose structure is so easier than amylopectin. And using a starch sources with large levels of amylose in their structures may be more advantageous for the melt spinning process. But high amylose content exhibits low to extremely low viscosity. And this is a big challenge for us, that we need a higher amount of amylose, but the viscosity is very low to extremely low. Balance between melt viscosity and drawability of the molecular chains during the melt spinning process is very, very important for us. So, as our study in some variant reference, you can see the table: normal corn, waxy maize, high amylose corn, potato, tapioca, and wheat. And among these starch sources, you can see the normal corn and wheat have a relative viscosity, medium or near to medium viscosity. Maybe both of these sources is suitable for melt spinning. Why native starch is unsuitable to using melt process like as melt spinning process? We have three reasons: complex macromolecular structure, huge extent of hydrogen bands, low thermal degradation temperature. So, to overcome starch limitation, we need to thermoplasticization of starch. Thermoplasticization of the starch needs to applying plasticizers, for example, glycerin, sorbitol, and etc., heat and shear force. So after plasticization, TPS has a huge potential to improve PLA fibers biodegradability and compostability. So the TPS has a very good biodegradability and maybe can improve the biodegradability of PLA fibers in melt spinning. But immiscibility of PLA and TPS is a new challenge. PLA and TPS, both of them, one of them is hydrophobic, one of them is hydrophilic, and they have different melting points. So they are immiscible. Low interfacial adhesion and compatibility between the TPS and PLA forced us to using a compatibilizer agent. So with a compatibilizer agent, we can decrease the size of the TPS in the PLA. And with this shape of disperse phase, we can improve the interfacial adhesion between PLA and TPS, and maybe we can solve the problem of melt spinning and separation, phase separation of PLA and TPS throughout the melt spinnerets. As our study about different strategies to compatibilization of PLA and TPS by researchers, they reported 4 different categories: chemical cross-linking, amphiphilic bridging, componential modification, and interfacial transition. Among them, chemical cross-linking and some amphiphilic bridging may be more suitable for using the master batch of PLA TPS for melt spinning. You can see in the table some valuable experiments about different researchers. For example, chemical cross-linking with PLA graft maleic anhydride. You can change the disperse phase diameter from 5 to 13 micron to 1 to 3 micron. So Another one is oligolactic acid grafted starch. The TPS disperses with a smaller size and better distribution reported. So in amphiphilic bridging, decrease the particle surface and increasing the elongation of the thermoplastic material is very valuable for us. Thermoplastic material with a high elongation rate. And amylose grafted PLA increase the tensile strength of PLA TPS blend containing 60% by weight of TPS. So when you have a 60% of TPS in PLA with a successful result, you can decide to lower than 60%, for example, 30% in PLA is enough in melt spinning process. And you can take a very good result about the melt spinning in a higher speed of take-up spinning. But the majority of researchers on spinning fiber from starch have concentrated on electrospinning. That electrospinning is not an industrial method for producing the fiber in an industrial scale. And the most suitable and cost-effective method for producing polymer fiber on industrial scale is melt spinning, as you know. But most efforts to fiber melt spinning of TPS composition have been in the form of patent, as you can see in the table. All of the reported information about the starch-based melt-spun fibers is in the form of patent. And normally, I can say that melt spinning of bicomponent filament is so much easier than conventional method of melt spinning. And if you search in this table, you can see most of them is in the bicomponent fiber system. So when you have hydrophile and hydrophobe polymers, melt spinning in a bicomponent melt spinning machine is so very, very easier than conventional method with the internal mixing of the polymers. For the first time, Avila Orta and his or her colleagues in 2023 used melt extrusion to create blends of PLA TPS fibers as non-woven mat with melt blowing process, not melt spinning. There is a big difference between melt blowing and melt spinning, as you know. Chemical modification, they say, chemical modification of starch reduces the difference in viscosity and encourages blending, resulting in more homogeneous morphologies of PLA TPS blend fibers. But Mesken and his colleagues in 2024 recently published a successful result of the melt spinning of PLA TPS monofilament compound. They used conventional melt spinning method, but their extruder is not a conventional. They use only laboratory scale piston type extruder machine. And very low take-up speed, around 20 to 50 meters per minute. It's the same as wet spinning or dry spinning. And the melt spun fibers were found to have a diameter in the range of 117 to 160 microns. Although they published their images of melt spun fibers, there is no mention about the mechanical properties in their papers. So it was probably due to the lack of use of compatibilizer agent in their study. And finally, sorry, maybe the animation is not through here, but the PLA fibers have a huge share of bioplastic fibers, but it degrades very slowly in soil and water at room temperature. And our recommendation is blending with thermoplastic starch as a fast biodegradable polymer as an economical and effective method. Finding a balance between melt viscosity and drawability of the starch source molecular chain during the melt spinning process is very, very important. Balance between melt viscosity and drawability. So recommendation is using starch sources with high amylose content and medium melt viscosity. Adding a coupling or compatibilizing agent enhance the interaction between the PLA and TPS, and our recommendation for a future works using a chemical cross-linking method with a proper compatibilizer such as PLA grafted with maleic anhydride. And most efforts to fiber melt spinning of TPS-based composition have been done in the form of patents, and they use a bicomponent melt spinning. Or some recent work carried out with low speed spinning, melt spinning. And unsatisfying fibers mechanical properties result. So our recommendation is working on conventional melt spinning. Try hard for melt spinning of PLA and thermoplastic starch in a high speed, not in a low, around 100 or lower than 100 meters per minute. So adding some nanomaterials like as nanocellulose can be improved thermal degradation of TPS. Your attention is greatly appreciated, and I'm ready to hear your suggestion or recommendation for our future study. Thank you.
Any questions? Go ahead, please.
Thank you so much. Very nice. And the target actually is going to be perfect.
Can we use the microphone? It's coming.
Thank you, sir. Thanks a lot. It was perfect, and I'm sure the result will be perfect too. And my question is that, you know, nowadays, for example, Corbion is advertising that the PLA is going to be degraded in 22 days. For example, tea bags are going to be degraded in 22 days compared to a banana peel, which takes, for example, more than 1 month. So they are comparing their degradation with the, for example, fruit peels, which is really biodegradable. So by getting to that point, I'm sure that they are talking about industrial, for example, composting situations. In your case, you are going to make it home compostable. So in room temperature, if something is going to be degraded, we can call it home compostable. And in that case, how it affects the serviceability of the plastic or fiber or anything. So is it going to be serviceable, for example, as a textile or as a packaging material? Because it degrades.
So as I understand about your question, you want to know about the difference between industrially compostable and home compostable.
No. Look, for example, at the end of the day, by incorporating starch into the PLA, you are increasing the biodegradability of PLA and making it biodegradable at room temperature. If it's true, then the product is not going to be serviceable. For example, we cannot make fibers because it will degrade, or any plastic out of it for packaging, it will degrade. So is it going to be, for example, workable for the actual product that we are looking for?
Related to, it depends to some factors that what application you want to use it. So when you want to use it to biodegradation in a long term, so you need the pure PLA fibers. Sometimes you need to faster biodegradation, and this time you need to PLA with a higher biodegradation rate. So the PLA fibers normally have a very long-term biodegradation, as I said, maybe in several months for fully biodegradation. And I think several years in the normal condition, not in the industrial condition. So we must see to what we want to apply the product for which kind of products. And we can use many different ratio of, for example, thermoplastic starch in PLA, and produce a very flexible products with a different time of biodegradation. And the blending is a very good ways to organize or plan your products for the market. Can I?
Okay. Yeah, of course. Thanks a lot. Thanks.
Any other question? Go ahead, please.
Thank you very much, Professor Tanya. When you are talking about starch, these are, well-known, common, conventional sources of starch, which is used in commercial and available. But when you talk about starch, we have to take notice. One group that stands out is all these starch sources. This is called Vaccaria hispanica, cow cattle. It is
excuse me, Vaccaria
hispanica.
Cow
cattle.
Cacao.
Yes, cow cattle. Yes. Yeah. It is the natural crop around here. It is a good source of starch. The starch diameter size 1/10 of this is conventional starch. I don't know the exact chemical analysis, what's the percentage of amylose and amylopectin, but we have to try to, this is totally different and starch properties that may serve for your purpose. Because of this ultra small starch size, it is used in making creams and other things. Now there are, there are teams working on this one in Turkey also. They are trying to commercialize breeding new varieties with, a high starch or something like that.
Thank you. Absolutely, I will study about it because it may be a good solution for finding the best source. So, but we must attention to product capacity and the cost of the starch. This is important.
This is important, yeah. Of course. Yes.
But absolutely, we will study about your suggestion. Thank you.
Yeah, this is totally different starch source anyway.
Yes.
Thank you very much.
Any other question?
Thank you, Dr. Tavanay. It was a very nice presentation. I might have just a complimentary answer for the question by Dr. Mansour. I think by changing the ratio of starch, you can tune the biodegradation rate, and also in contrast the surface life, and these might be very interesting for temporary applications, like, I don't know, maybe a solution for non-wovens, even spunbonds and so on, in continuing of this work. But regarding your remark about bicomponent, what do you think? I don't think bicomponent is very interesting.
Yeah.
I have the reason for that, because you need to put the starch in the core.
Yeah, exactly.
Am I true?
Exactly.
But biodegradation is a surface
From
activity.
the surface.
Yeah.
So I think bicomponent fibers production capacity in the world is very, very lower than the conventional method melt spinning. And the bicomponent melt spinning was done previously, and there isn't any issue or there isn't any challenge between the researchers now. And the big challenge in melt spinning. For electro spinning, starch is very easy. So about wet spinning, dry spinning, all of them is so easier than melt spinning. And the big challenge is in the melt spinning and thermal degradation of the TPS in the melt extrusion temperature. Thank you very much.
Okay, maybe we have time for one more question. All right, thank you very much.
Thank you. So I want to give my thanks to organizing committee, especially Dr. Bilaki, my dear friends, and Professor Yusuf Olcay from Bursa Technical University. Thank you, and Mr. Demir, dear Ali Demir. Thank you.
Well, this concludes our session. Thank you for coming, and have a good rest of the day.